Many people know about the International Space Station or the new missions to Mars. But humanity has sent out so many space missions, trailblazers of various era: Voyager, Venera, Messenger, and others. Quite a few are still out there, forgotten machines from an earlier age of exploration, quietly orbiting, tumbling through interstellar space, or frozen in the shadows of alien worlds. These ghost satellites are time capsules, drifting reminders of our first steps into the unknown. Let's uncover their stories, where they went, what they discovered, and why they still matter, even as they fade into the cold shadows of deep space. An empire's first footsteps, the Soviet Union's early space relics. Thinking of the space race conjures up images of rockets launching into the unknown, astronauts floating in orbit, and flags planted on distant worlds. But long before the moon landings, there were smaller, quieter beginnings. Machines that didn't carry people, satellites that didn't come back. These were the first steps of an empire into space. Many of those first Soviet satellites, launched in the late 1950s and early 1960s, are still up there today, forgotten by most, drifting in silence. The story starts with Sputnik, the first artificial satellite ever launched. On October 4, 1957, the Soviet Union shocked the world by sending this small, round metal object into orbit. It was about the size of a beach ball, and its only job was to send out a radio beep. But that beep echoed across the globe. The Soviets had reached space first. The Cold War had entered a new phase. Sputnik 1 itself only lasted 21 days before its batteries died. A few months later, it fell back into Earth's atmosphere and burned up. But Sputnik wasn't alone. It was followed quickly by Sputnik 2, which carried the first living creature into orbit, a dog named Laika. That satellite did not come back. Its systems failed within hours, and it remained in orbit for over 5 months before re-entering the atmosphere. Then came Sputnik 3, a much heavier scientific satellite, loaded with instruments to study radiation and cosmic rays. This one stayed in orbit much longer. For many years, its metallic body quietly circled the Earth, long after it stopped transmitting. No one controlled it anymore. No one listened for its signals. But it remained part of the sky. Throughout the late 1950s and early 1960s, the Soviet Union launched a long series of satellites under names like Cosmos, Vostok, Luna, and Molniya. Some were used for scientific research. Others were military in nature, testing radar, spying on Earth, or relaying communications. Most of them stayed in low or medium Earth orbit, and many of them, once their jobs were done, were simply left in space. The Cosmos program alone is vast. The name was used by the Soviet Union for hundreds of different satellites, many of them classified. Some were experimental platforms, others disguised weapons tests or early warning systems. Because of their secretive nature, many of these satellites weren't even acknowledged by the Soviet government at the time. They were launched under cover of night, tracked by Western radar, and logged into military databases. There are also the early lunar missions. These probes were designed to reach the moon, but not all of them made it. Some failed during launch and fell back to Earth. Others reached Earth orbit, but couldn't escape its gravity. A few became unintentional ghost satellites, machines built to go farther, but stranded just above our planet. Without the fuel or guidance systems to correct their course, they remained in low orbit, dead from the start. In 1960, the Soviet Union also began launching Vostok spacecraft, the same type later used to carry cosmonauts like Yuri Gagarin into space. Before sending people, the Soviets tested the system with unmanned versions. These test flights used full-size capsules, complete with life support systems and telemetry equipment. Some failed and never made it into the proper orbit. Others succeeded, orbited Earth, and were recovered. One rarely discussed category of Soviet satellites is RORSATs, or Radar Ocean Reconnaissance Satellites. These were launched between the 1960s and 1980s and carried onboard nuclear reactors. Unlike most satellites, which run on solar panels or batteries, RSATs needed constant power to operate their radar systems. After they finished their missions, most of these satellites ejected their nuclear cores into higher orbits, but the rest of the satellite, the body and radar systems, remained in low Earth orbit. Many of them are still there, considered some of the most dangerous ghost satellites due to the risk of collision and the radioactive materials they once held. Some of the earliest Soviet communication satellites were from the Molniya program. These followed a unique elliptical orbit that allowed them to cover northern regions for long periods. Important for a country with such vast territory near the Arctic Circle. These satellites would climb high above Earth and then drop down, over and over, in a long oval path. Dozens of Molniya satellites were launched. Tracking these old satellites isn't easy. Many were launched with little or no public documentation. Some had their orbital data classified, others changed course slightly after launch or during their operational life. Over the decades, many of these ghost satellites blended into the background of space. Modern radar systems, both civilian and military, have tried to identify and catalogue them. But it's a slow process. And because these satellites no longer transmit signals, they must be located visually or through reflected radar pulses, which takes time and effort. Amateur satellite watchers have played a role in rediscovering many of these lost Soviet objects. Using ground-based telescopes, radio receivers, and online tracking tools, they've identified dozens of old Soviet satellites still moving overhead. Some have even managed to photograph them, capturing images of these metal relics as they pass silently across the night sky. The Cold War rivalry that launched these satellites may be over, but its legacy remains above us. The Soviet Union raced to space with purpose and pressure, aiming to demonstrate power, skill, and ambition. In doing so, it left behind a fleet of machines that no longer serve, no longer respond, but still endure. What remains of Salyut 1, the first space station in history? Salyut 1 was the first space station ever launched by humans. It marked the beginning of a new kind of mission, one where people would not just visit space for a few hours or days, but live there. Launched by the Soviet Union on April 19, 1971, it was a major step forward in space exploration. But the station's life was short, and its story ended in both silence and sorrow. The idea behind Salyut 1 was to create a place where cosmonauts could stay for weeks at a time, carrying out scientific research and learning how the human body handles long-term weightlessness. The station was over 15 meters long and weighed more than 18 tons. From Earth, it looked like a long metal cylinder with solar panels sticking out from its sides. Inside, it had work areas, sleeping quarters, and even a small kitchen. It was cramped, but it was the first of its kind. After its launch, the Soviet Space Agency prepared to send a crew. On April 22nd, 3 cosmonauts lifted off aboard the Soyuz 10 spacecraft, intending to dock with Salyut 1, but things didn't go as planned. The docking mechanism failed. Though they reached the station and got close enough to touch, they couldn't lock on. The crew had to come home without ever entering the station. The mission was a disappointment, but not a disaster. Then came Soyuz 11. Launched on June 6, 1971, the Soyuz 11 crew, Georgy Dobrovolsky, Viktor Patsayev, and Vladislav Volkov, successfully docked with Salyut 1. They entered the station, becoming the first people in history to live aboard a space station. Over the next 23 days, they worked hard. They ran medical experiments, observed Earth, and tested the station's systems. It was a major milestone for the Soviet space program. But tragedy followed. On June 30, 1971, the crew prepared to return to Earth. They undocked from Salyut 1 and began re-entry. But during descent, something went wrong. A cabin vent valve opened early, and the capsule lost pressure. All 3 men died silently in their seats. Ground control only discovered the disaster after landing, when recovery teams opened the capsule and found all 3 cosmonauts dead. They were the first, and still the only, humans to die in space beyond Earth's atmosphere. After the loss of Soyuz 11, the Soviet Union never sent another crew to Salyut 1. The station remained in orbit for a few more months. With no one aboard, it drifted silently above the planet, still whole but unused. Engineers tried to maintain contact, but with no crew to run systems or perform maintenance, it couldn't last. On October 11, 1971, the station was guided into a controlled re-entry. Most of it burned up in Earth's atmosphere over the Pacific Ocean. Its mission was over, and the Soviet Union made sure it would not become a long-term hazard. Still, its story did not end with fire. Pieces of it may still lie at the bottom of the ocean. While no large chunks are known to be still circling Earth, small fragments could have separated during docking, undocking, or even during its launch. These are not tracked closely. They are too small to pose much danger, but they are part of the larger field of debris around our planet. Pieces of history drifting unseen. The design of Salyut 1 lived on. Though the station itself was gone, the Soviet Union used its blueprint to build more advanced versions. Later stations like Salyut 6, Salyut 7, and eventually Mir were all based on lessons learned from this first mission. Even the International Space Station orbiting Earth today carries echoes of what started with Salyut 1. Modular parts, long-term habitation, docking ports. These are ideas that began in that metal tube from 1971. The loss of Soyuz 11 made engineers rethink safety. Later, Soyuz capsules were redesigned. Crews would now wear pressure suits during launch and re-entry, something they hadn't done before. Vent valves and other systems were made safer. It was a painful lesson, paid for in lives, but it changed the way humans go to space. When we think of ghost satellites, we often picture silent probes or old weather satellites. But crewed missions also leave ghosts behind. Not just machines, but memories. Salyut 1 was only in space for 175 days. Only 1 crew ever entered it. Yet it changed everything. It proved that humans could live and work in space for extended periods. It showed what was possible and what could go wrong. People sometimes forget Salyut 1. It's not as famous as Skylab or Mir. Its name doesn't appear in many headlines, but above the Earth, during that strange summer of 1971, it floated quietly, holding 3 men who gave everything in the name of progress. The station had no windows facing Earth. Its views were mostly outward, toward the stars, toward space itself. There is no grave marker for Salyut 1, no orbiting memorial. Yet for those who study space history, it stands as the first real home humans ever had beyond Earth. A home that floated briefly, held life, and then was gone. Its name, Salyut, means salute, a gesture of respect, and that, in the end, is what it deserves. Skylab, NASA's forgotten orbital laboratory, still falling through time. Skylab was America's first space station, and for a short time in the 1970s, it represented the height of NASA's ambitions in low Earth orbit. It was larger than anything that had ever been launched before. Unlike the Soviet Salyut stations, which were compact and tube-shaped, Skylab was broad and cylindrical, designed to allow astronauts to move around more freely inside. It had windows, lab space, even a shower. Small luxuries meant to help people live and work in space for longer periods. But despite its size and promise, Skylab's life in orbit was short, and its end was messy and unexpected. Launched on May 14, 1973, Skylab had started out as part of the Apollo program. NASA used parts left over from the moon missions to build it. The main structure was a converted Saturn V rocket stage, hollowed out and fitted with science gear, solar panels, and living quarters. It was a clever use of hardware, turning the tools of lunar exploration into something new, a floating science lab. But Skylab's problems began almost immediately. Just 63 seconds after launch, a micrometeoroid shield that also acted as a heat shield tore off due to vibrations and air pressure. One of its solar arrays was ripped away, and the other was jammed shut. Without proper power or shielding from the sun, the station began overheating. Internal temperatures soared, making it unsafe and unusable unless something was done quickly. 10 days later, a crew of 3 astronauts launched aboard an Apollo spacecraft to save it. They brought tools, spare parts, and even a makeshift sunshade, a large sheet of material they managed to stretch across the outside of the station to block sunlight and lower the internal temperature. It worked. Power was restored. Skylab became usable again. 3 crews would visit Skylab between 1973 and 1974, each staying for longer than the last. The final group lived aboard for 84 days, breaking records for human time in space. Inside, the astronauts carried out experiments in medicine, physics, solar observation, and Earth studies. They took thousands of photos of our planet and the Sun, capturing solar flares in detail never seen before. They also faced the day-to-day challenges of life without gravity, learning how the human body adapts over time. Skylab showed that extended space missions were not only possible, but productive. But while the work went well, the station's long-term fate was already being sealed. Not by technology, but by time, budget cuts, and a changing political landscape. NASA had hoped to revisit Skylab in the early 1980s using the Space Shuttle, which was still being developed at the time. Engineers believed the shuttle could dock with Skylab, raise its orbit, and even reuse parts of it. But delays in the shuttle program stretched on for years. Meanwhile, Skylab's orbit was decaying. Though it had been placed high above the Earth, it was still within the reach of the atmosphere's outer layers. Drag slowly pulled it downward, little by little. Then came something no one had counted on: the Sun. In the late 1970s, the Sun became more active than expected. Its increased output heated the Earth's upper atmosphere, causing it to expand. That extra heat and expansion added more resistance to Skylab's orbit, speeding up its descent. NASA scrambled to respond, but by then there was no way to reach the station in time. The shuttle wasn't ready, and there were no rockets available to boost Skylab to safety. NASA knew the station would fall. The only question was when and where. For months, the agency tracked Skylab's orbit and tried to narrow down the moment of re-entry. They issued warnings, sent updates to governments around the world, and hoped the station would break up safely over the ocean. But no one could predict it exactly. On July 11, 1979, Skylab finally re-entered Earth's atmosphere. The giant station began to break up high above the Indian Ocean, with debris falling along a wide path that extended over parts of Western Australia. Some pieces burned up, but others survived. Metal fragments, tanks, and parts of the lab's frame rained down onto remote areas. No one was hurt, but the incident became a global news story. It was the largest uncontrolled re-entry of a man-made object at the time. Locals found pieces of Skylab scattered across the desert. A town in Australia fined NASA $400 for littering as a joke. Souvenir hunters collected debris. Some of those pieces are still in private collections or museums. And though most of the station was destroyed during re-entry, some parts may still rest today where they fell, weathered by time but not forgotten. The fall of Skylab highlighted the risks of putting large objects into space without long-term plans for their removal. Unlike Salyut 1, which was guided back down in a controlled descent, Skylab had no way to steer itself. NASA learned many lessons from Skylab. Later missions, including the International Space Station, were designed with clearer plans for orbit control and safe deorbiting. But back in the 1970s, these systems were still being figured out. Skylab wasn't part of a long series. It didn't get a second version or a follow-up station. It was one big shot, an experiment in how far America could go with the tools it had left over from Apollo. When the Space Shuttle finally launched in 1981, Skylab was already gone. The two programs missed each other by just a couple of years. Skylab was the bridge between eras. It proved that people could live and work in space not just for days, but for months. It taught engineers how to build big, habitable structures in orbit, and though it fell from the sky, it left behind a trail of knowledge and warnings. Luna and the Long Silence, Soviet landers on a lifeless moon. They sit in silence under a sky that never changes. These are the Lunar Landers, left behind by the Soviet Union more than half a century ago. They remain motionless and untouched on the moon's surface, where no wind or rain will ever wash them away. The lunar program marked some of the earliest and most daring steps in space exploration. The Soviet lunar program began in the late 1950s, during the height of Cold War competition with the United States. It was one of the first major efforts to reach and study the moon. While American missions were still preparing to orbit Earth, the Soviets were already launching probes designed to strike the moon's surface, or, if possible, to land softly on it. Most of these early attempts failed, but the failures told scientists what needed to change. Each mistake pushed the design forward, step by step, towards success. In 1959, Luna 2 became the first human-made object to reach the moon, crashing into the surface and ending its mission in a cloud of dust. It was a hard impact, not a landing, but it made history. Just weeks later, Luna 3 flew past the moon and sent back the first images of the far side, areas never seen from Earth. These early missions did not survive for long, but they taught the Soviets that the moon could be reached. Then came Luna 9 in 1966. This was the breakthrough. It became the first spacecraft in history to make a soft landing on the moon and send back photos from the surface. Unlike crash probes or flybys, Luna 9 touched down gently using retro-rockets, airbags, and a carefully timed descent. Once settled, its petals opened like a mechanical flower, revealing a small camera inside. The images it sent showed a flat, dusty surface and a black sky. There were no hills in sight, no signs of movement, but for the first time, people on Earth could see what it looked like to stand on the moon. Over the next decade, the lunar program launched dozens of similar landers, some successful, others not. Luna 13 in 1966 followed with better cameras and soil sensors. Luna 16, 20 and 24 performed something even more complex. They drilled into the lunar ground, collected samples and sent them back to Earth. These were robotic missions, fully automated, using early computers and remote programming. There were no astronauts, no voice contact, just quiet signals sent across nearly 400,000 kilometers of space. Unlike orbiters, these landers remain fixed in one spot. They are still there, sitting exactly where they came to rest, slowly collecting dust. The moon has no atmosphere to wear them down, no weather to scatter their pieces. Their metal frames may be cracked from cold, their solar panels faded from decades of radiation, but they are otherwise unchanged. To this day, they are time capsules, untouched machines from a lost era of exploration. Some of these landers were truly advanced for their time. Luna 17 and Luna 21 carried robotic rovers known as lunokhod that explored the surface using wheels, cameras, and remote control. Lunokhod 1, which landed in 1970, was driven from Earth in real time, moving across the moon's surface and transmitting hundreds of images. It was the first rover ever to operate on another world. The Soviets had achieved this without ever sending a human to the moon. Their robots did the work silently, carefully, across several kilometers of unknown terrain. But while these missions were impressive, they did not last long. Most lunar landers functioned for days or weeks before falling silent. Power systems failed. Electronics wore out. Temperatures dropped far below freezing during the lunar night, cracking sensitive parts. Once a lander's system shut down, they never restarted. There were no maintenance crews and no recovery plans. Once contact was lost, it was lost forever. The last lunar mission, Luna 24, landed in 1976. It dug into the surface and returned a small core sample, 170 grams of moon dust and rock. It marked the final chapter in the Soviet lunar program. After that, the focus shifted elsewhere, to Mars, Venus and Earth's orbit. No more lunar craft were sent. The landers already on the moon were left behind, their tasks complete. Modern lunar missions have occasionally photographed these old machines. Lunar Reconnaissance Orbiter, launched by NASA, captured detailed images of lunar landers and their rover tracks. In some cases, the Lunokhod rover paths are still visible, etched into the dust like trails left by an ancient traveller. The moon holds no storms. Every wheel print remains just as it was laid down decades ago. These photos are the only proof that these machines are still there. From Earth, the landers are too small to see. Their signals have long stopped, but they remind us that once, before GPS, before smartphones, before space shuttles and space stations, people built machines and sent them to another world. In many cases, the Soviets launched without knowing for sure what would happen. The terrain was unknown. The software was primitive. Delays or mistakes could ruin a mission completely. And yet they kept trying. Each success was hard-won. Each failure was a lesson. There is a kind of honour in these quiet machines. They proved that robotic exploration was possible, even with limited tools. And they showed that even in the midst of Cold War tension, science could reach beyond Earth. In a way, these landers are the ancestors of the many robotic explorers that followed. Rovers on Mars, landers on comets, probes around distant planets. Each one owes something to the lunar program, to the engineers and scientists who dared to aim for the moon with machines made from wires, gears, and hope. Dead on arrival, the Venera missions that melted on Venus. The surface of Venus is hot enough to melt lead, the air thick with choking clouds of sulfuric acid, and the atmosphere so heavy that it crushes most machines sent from Earth. For decades, it remained nearly unreachable, not because of its distance, but because of its hostility. Still, the Soviet Union tried. Again and again, they sent robotic probes to the second planet from the Sun. These were the Vanera missions, bold attempts to land on a world that seemed purpose-built to destroy them. The Venera program began in the early 1960s, part of the same wave of Soviet exploration that produced Luna, Sputnik, and the first crewed flights into space. Venus was chosen because it is Earth's closest planetary neighbour. Seen from Earth, it shines brightly in the evening or morning sky, a glowing white light. But its beauty hides a deadly truth. Long before humans understood how severe Venus's environment really was, Soviet scientists believed it might be similar to Earth, perhaps cloud-covered, perhaps humid, but still familiar. The first Venera probes never got close enough to find out. Many failed during launch. Some lost contact before they even left Earth's orbit. Others missed Venus entirely, drifting silently through space. But with each failure, engineers learned. They strengthened structures, improved navigation, and designed better heat shields. In 1967, Venera 4 became the first probe to enter Venus's atmosphere and send back data. It didn't reach the surface, but it changed everything. It showed that Venus was far more dangerous than expected. The temperatures were higher. The pressure was extreme. What was thought to be a cloudy, possibly ocean-covered world turned out to be a kind of hell. The air was mostly carbon dioxide. The clouds contained sulfuric acid. The crushing pressure at the surface was over 90 times that of Earth, comparable to being a kilometre under the ocean. Venera 4 was destroyed mid-descent, its thin metal hull unable to handle the weight of the air. Venera 5 and 6 followed, also entering the atmosphere, but again neither survived the descent. Then came Venera 7 in 1970. It was heavier, with a reinforced hull and a tighter shape. The parachute was modified to drop faster, giving the probe less time to be damaged before touchdown. Venera 7 landed, and for a short time, it lived. It became the first spacecraft to transmit data from the surface of another planet. Only 23 minutes of radio contact were achieved before it failed, its electronics overheating in the blistering air. But it had survived long enough to prove it could be done. The missions that followed kept pushing the limits. Venera 8 lasted 50 minutes. Venera 9 and 10 sent back the first images of the Venusian surface, blurry, grey scenes of broken stones under a cloudy sky. The horizon was shrouded in haze. There was no sunlight, just a thick orange glow. The rocks were flat and lifeless, but these were pictures no one had ever seen before, sent from a place where the temperature reached 470 degrees Celsius. Inside these probes, every second counted. Once they hit the surface, the clock started ticking. The heat baked their circuits. The pressure squeezed their frames. Cooling systems failed quickly. Internal parts began to warp and melt. Each Venera lander was designed to endure just long enough to tell Earth what Venus was like before dying in silence. Venera 13, launched in 1981, was one of the most successful. It lasted over 2 hours. Its cameras showed a world coated in dust and scattered rocks. The images were orange tinted, not from the filters, but from the sky itself, which glows orange from the thick, choking atmosphere. Venera 13 also recorded sounds. It was the first time humans had ever heard anything from the surface of another planet. The recording caught the rush of wind, the hiss of gas, and the dull, mechanical noise of the probe's own systems. Brief, eerie moments before the silence returned. Venera 14, nearly identical, returned similar data. Its soil sampler arm tried to scoop the ground, but it happened to hit its own ejected lens cap, so the sample was lost. Even so, it too sent valuable information before it failed in the heat. Venera 15 and 16 stayed in orbit, mapping the surface with radar from above, since the thick clouds prevented normal photography. The Venera landers had no solar panels, no way to cool themselves beyond basic insulation and internal tanks. Once their systems overheated, they would never work again. Unlike the Lunar Landers, which remained sitting quietly in the cold, dry dust of the Moon, the Veneras met a violent end. Their circuits burned, their wires twisted and melted. Their hulls may have even collapsed under the pressure. They are still there, buried under the weight of the thick air, but they are not intact. They were destroyed in place, consumed by the world they touched. Some estimates suggest that the metal in their frames slowly fused, warped by the high heat. Others say the corrosion from acidic gases may have eaten through them over time. No one knows for sure, because no mission has returned to see them. Unlike the Moon, where we can photograph old landing sites, Venus hides its dead beneath a thick, permanent veil. The Venera landers are invisible, their remains distorted and buried, far beyond human view. Theirs is a story of violence and endurance. Their final moments were filled with heat, noise, and system failures. But they did their work. They sent back signals, pictures, and data from one of the most hostile places in the solar system. In many ways, they paved the way for what we now call extreme environment missions. They taught engineers how to design for heat and pressure. They showed that survival, even for a short time, was possible. Modern space agencies still refer to Venera data when planning new missions to Venus. And some, like the upcoming Veritas and Envision projects, hope to return, not to survive the surface, but to observe it from orbit, learning through radar and remote sensing rather than direct contact. For now, the Vanera Landers remain unreachable. These were ghosts forged in fire, the remains of a time when humans dared to reach down into a planet that burns. They were the first, and for now, still the only machines to speak to us from the surface of that hidden, violent world. Pioneers in the outer dark. Where are Pioneer 10 and 11 now? In the early 1970s, two small spacecraft were launched into the sky with a goal no machine had ever tried before. These were Pioneer 10 and Pioneer 11, NASA's early scouts to the outer solar system. Pioneer 10 launched first on March 2, 1972. Its mission was simple but ambitious: reach Jupiter, pass through its harsh radiation belts, and send back close-up images. No spacecraft had ever gone that far. Until then, Jupiter had been seen only through telescopes. Distant, cloudy, mysterious. Pioneer 10 made the journey in just under 2 years. On December 3, 1973, it flew past Jupiter at a distance of about 132,000 kilometers. It sent back detailed pictures of the planet's storms, moons, and magnetic field. It survived the trip through intense radiation and left Jupiter behind. Its job done. But the story didn't end there. With no planets left to visit, Pioneer 10 continued on its path, pulled only by gravity and pushed by the silent momentum from its launch. It passed the orbit of Saturn, then Uranus, then Neptune. It kept going, heading out of the plane of the solar system, travelling in the direction of the constellation Taurus. No steering system, no course correction. Just a quiet flight into darkness. Pioneer 11 followed a year later, launched on April 5, 1973. It had a similar goal, but a different path. It too flew by Jupiter in 1974, using its gravity to bend its course towards Saturn, something never done before. In September 1979, Pioneer 11 became the first human-made object to visit Saturn, flying just 21,000 kilometers above the cloud tops. It returned photos of Saturn's rings and confirmed the planet's strong magnetic field. Like its twin, it was built tough but basic. Its instruments were designed in the 1960s. Its memory was measured in kilobytes. Yet it worked, and after its planetary tour, it too left for deep space. The farther they travelled, the fainter their signals became. NASA continued to track them for many years. Pioneer 10's signal was last received on January 23, 2003. At that time, it was more than 12 billion kilometres from Earth. The signal was incredibly weak, just a whisper against the static of the universe. It took over 11 hours for the radio waves to reach Earth, but it still spoke. Pioneer 11 stopped communicating earlier. In 1995, contact was lost. It was heading in a different direction, toward the constellation Scutum. Its power was gone. Its systems shut down. It had no fuel, no solar panels, and no hope of being woken again. But like its twin, it didn't need to be alive to keep flying. Today, both Pioneers are still moving, slowly and silently, away from everything we know. They are no longer part of the solar system in the usual sense. They have passed the orbits of all known planets. They are moving through the outer regions of the heliosphere, the bubble of space influenced by the sun's solar wind. Beyond that lies interstellar space, where the pressure from other stars becomes stronger than our own suns. It will take many thousands of years for them to reach those distant places. But they are heading there, drifting along paths set decades ago. Each spacecraft has a small, gold anodized aluminum plaque, bolted to the side of the frame. The plaque was designed by Carl Sagan and Frank Drake, with artwork by Linda Salzman-Sagan. It shows a man and a woman, drawn in simple line figures, along with the spacecraft behind them for scale. There is a map showing the position of Earth in relation to pulsars, and a drawing of the solar system with the Pioneer's route marked. This plaque is not a scientific tool. It is a message, a greeting from a planet orbiting a small star sent into the dark in case someone, someday, finds it. The odds are almost impossible. Space is vast beyond imagining. Even after 1 million years, these probes may not pass close to any star. But the plaques are there, just in case. Pioneer 10 is heading toward the red dwarf star Ross 248. If it continues in a straight line, it will pass near that star in about 2 million years. But it will not be moving fast enough to escape the galaxy. One day, far in the future, gravity will slow it, and it will begin a long, looping orbit around the Milky Way. It will remain a silent passenger of our galaxy, possibly for billions of years. There is no camera to track them now. No light shines on their paths. They are beyond help, beyond command, yet they are not lost. Their locations are roughly known, their paths modelled by physics and mathematics. They remain among the quietest ghosts in space, no longer sending signals, but still remembered. The spacecraft themselves are likely still intact. The vacuum of space means little erosion or rust. There is no wind, no water, no weather. Their metal frames may have cooled to near absolute zero. Their gold plaques may still shine, untouched by dust or time. Inside, the wires and circuits are frozen in place, as if caught in mid-thought. The radioactive power sources, once glowing with heat, have faded to near silence. The idea that we sent these small machines so far, and that they are still going, says something about human vision. They were made in labs with limited budgets and short timelines. But their journey outlasted every plan. Voyager's eternal drift, the soundtrack of humanity, heads into the unknown. In the summer of 1977, 2 spacecraft were launched one after the other. Voyager 2 lifted off first, followed a few weeks later by Voyager 1. They carried instruments, cameras, sensors and commands to explore the outer planets. But they also carried something else. Attached to the side of each Voyager was a small golden disc. It was a message, a recording, a kind of time capsule meant for the stars, a greeting from Earth to the unknown. The Voyager missions were built on the success of Pioneer, but they aimed higher. Thanks to a rare alignment of planets that happens only once every 176 years, the Voyagers were able to use a technique called gravity assist. Each spacecraft would fly past one planet, gain speed from its gravity, and move on to the next. Voyager 1 visited Jupiter and Saturn. Voyager 2 made the full tour. Jupiter, Saturn, Uranus and Neptune. No spacecraft has done that since. At each stop, the Voyagers returned images that stunned the world. Volcanoes on Io, rings around Jupiter, storms on Saturn, icy worlds at the edge of sunlight. The photographs were sharp, the data rich. Scientists learned about magnetic fields, atmospheric chemistry, and hidden moons. But eventually, the planets were behind them. Like the pioneers before them, the Voyagers moved on into deep space. And they kept moving. By 1990, their main planetary missions were complete, but their journey was not over. As their instruments aged, engineers reconfigured them to keep working longer. One by one, systems were turned off to save power. Even now, they still send back data, faint signals caught by the Deep Space Network, giant antennas on Earth that listen for whispers from the farthest places. Today, Voyager 1 is the farthest human-made object in existence. In 2012, it crossed the boundary of the heliosphere. It entered interstellar space, no longer under the direct influence of our star. Voyager 2 followed in 2018, crossing that same line. They are now travelers between stars, moving into a realm that no other machine from Earth has ever entered. Voyager 1 is heading toward the constellation of Ophiuchus. Voyager 2 is heading towards Sagittarius. It will take tens of thousands of years for either to come close to another star. Their power sources, radioactive generators, are slowly fading. By 2030 or shortly after, they may fall silent. The signals will stop. But the spacecraft will not. They will keep drifting, still carrying the message they left with. The golden record is what sets the Voyagers apart. It is a 12-inch gold-plated copper disc mounted to each spacecraft beneath a protective aluminum cover. On the cover is a diagram, how to play the record, where Earth is, how fast to rotate the disc. Inside are 115 images, greetings in 55 languages, sounds of Earth, and 90 minutes of music. Among the recordings are a baby's cry, a kiss, thunder, laughter, and the sound of a heartbeat. There are animals, trains, a blacksmith at work, and footsteps on dry earth. The music is wide in range. There is Bach and Beethoven, but also a Navajo chant, a Bulgarian folk song, Japanese shakuhachi flute, and songs from Senegal and Peru. One track features a blind girl's song from Azerbaijan. Another includes a raga by Indian sitar master Ravi Shankar. The idea was not just to show what we sound like, but what we feel. Carl Sagan, who helped lead the team that created the record, called it a bottlecast into the cosmic ocean. It was not a message to anyone in particular, just a way of saying we were here. Also included was a printed message from the then President of the United States, Jimmy Carter. It reads, "This is a present from a small distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. We are attempting to survive our time so we may live into yours. There is no guarantee anyone will ever read those words, but they are there, waiting." The Voyager's path is guided only by the original thrust of launch and the subtle pulls of distant stars. There is no fuel to adjust their course. Their batteries, powered by plutonium, grow weaker each year. Engineers at NASA carefully decide which instruments to shut off, which systems to keep running. The heat drops, the electronics slow, but still they speak. The Deep Space Network must listen very carefully to hear them. Each signal from Voyager 1 now takes over 22 hours to reach Earth. The strength of the signal is less than a whisper against the static of the galaxy. It is like trying to hear a watch ticking from across the continent, but the signal carries data about cosmic rays, plasma waves, magnetic fields, traces of the space between stars. No other spacecraft has been as far. None has lasted as long. Both Voyagers have been in flight for nearly 50 years. When launched, they carried technology that was already out of date. Computers with less power than a pocket calculator. And yet they have outlived almost every machine ever made. They were built with care, with backups and redundant systems, but also with limits. Their cameras have long been turned off. Their heaters are failing. And yet, they continue. There is something deeply human in the idea of these two spacecraft flying into darkness, carrying music and greetings and images of life. In time, even the gold plating may fade. Micrometeorites may pit the surface. Cosmic radiation may slowly eat away at the data. But for millions of years, maybe longer, they will keep moving. The odds of someone or something ever finding a Voyager are slim. Space is wide and almost entirely empty. Stars are far apart, and planets even more so. But if one day another civilization finds the golden record, they will hold in their hands a snapshot of Earth as it was in 1977. The hopes of a species, the sounds of a home, the laughter of people who sent their voices into space, never knowing if anyone would hear them. Not all satellites decay in Earth orbit. Not all crash to the Moon or melt on Venus. Some leave entirely, like a message thrown across a silent canyon. The Voyagers are proof that even in the emptiest reaches of space, something human can still remain. And that, for a moment, we reached outward, not for war or conquest, but simply to say hello. Shadows behind the comets, the lost path of the International Cometary Explorer. Launched in 1978, the spacecraft that would eventually be known as the International Cometary Explorer was not built for comets. Its original name was ISE-3, the third satellite in the International Sun-Earth Explorer series. It was part of a trio sent to monitor the flow of solar wind between the Earth and the Sun. At the time, this was new territory. Scientists wanted to understand how charged particles from the Sun affect Earth's magnetic field, how solar storms travel through space, and how space weather forms. IC-3 was positioned at a point called L1, about 1 million miles from Earth in the direction of the Sun. It became the first spacecraft to orbit around a Lagrange point, where the gravity of the Earth and the Sun balanced just right. There, it quietly kept watch. For the first few years, ISE-3 carried out its mission well. It returned data on solar wind, magnetic fields, and plasma interactions. But by the early 1980s, the spacecraft had already outlived its expected lifespan. Most missions would end at this point. Yet engineers and scientists realized it still had potential. They gave the aging satellite a bold, new purpose. IC-3 would become the first spacecraft to encounter a comet. This was not a simple change. IC-3 had been designed for calm duty near Earth. Now it would need to fly through the wild tail of a comet, dodging debris and enduring radiation it had never been built for. First, it had to escape Earth's gravitational hold. This required several careful maneuvers, using the Moon's gravity over and over to sling it farther out. Engineers designed a path that pulled it into a new orbit around the Sun. On its way out, it passed through the Earth's magnetotail, giving one last round of data from its original mission. In 1983, it was renamed from ISE-3 to ICE, the International Cometary Explorer. This new name marked a rare change in purpose for a spacecraft already in space. It was not often that something designed for one job took on a mission in a different realm of science. ICE was now aimed at comet Giacobini-Zinner. Giacobini-Zinner is not a bright or famous comet. It's not like Halley's, which grabs the attention of the whole world. But it was chosen because its orbit was within reach. On September 11th, 1985, ICE flew through the tail of the comet. It was the first spacecraft in history to do so. The encounter gave scientists valuable information about the structure of a comet's tail, its interaction with the solar wind, and the speed of particles inside it. ICE survived the crossing, still working after years in space and a journey far beyond its original scope. After this, it continued on its path through space. In 1986, ICE passed near Halley's Comet, though not as close as other spacecraft like ESA's Giotto. But it provided support from a distance, sending back measurements of solar wind that helped scientists understand how Halley's tail was shaped. Over time, ICE moved farther from Earth. Its instruments kept working even though no more comet missions were planned. Eventually, in 1997, NASA officially ended contact with the spacecraft, but ICE was not dead. For years, it floated quietly through space. Like a retired worker who had outlasted every project, ICE remained on its own path. Then, in 2014, something unusual happened. A group of citizen scientists and engineers, calling themselves the ISE-3 Reboot Project, decided to try to contact ICE. They knew that its orbit would bring it close to Earth again, for the first time in decades. Using crowd-funded money, they worked with old mission data, studied its communication system, and got permission from NASA to attempt contact. The equipment NASA had used in the 1980s no longer existed, but the team located a large dish antenna in Puerto Rico at the Arecibo Observatory and used it to send a signal. To everyone's surprise, ICE responded. After 36 years in space, the spacecraft was still listening. The reboot project hoped to redirect ICE into a new orbit and possibly put it back into science work, measuring solar wind or monitoring space weather. But time had taken its toll. When the team attempted to fire the spacecraft's thrusters, the results were unclear. Analysis suggested that the spacecraft's nitrogen pressurant needed to push fuel to the engines had likely leaked away. Without it, the thrusters couldn't work. ICE had the heart to go on, but not the lungs. Despite this, the attempt brought renewed attention to a long-forgotten mission. For a moment, ICE had spoken again. The team collected what data they could, listened to the final transmissions, and watched as the spacecraft moved on. There were no more maneuvers left to make. ICE passed Earth and headed away once more, continuing on a path around the Sun, in an orbit that may last for centuries. The story of ICE is different from that of Voyager or Pioneer. ICE began with its gaze fixed inward, toward the Sun, then turned outward, toward a comet. It crossed disciplines, from heliophysics to planetary science. It adapted mid-mission. Its transformation was not planned when it left Earth. It was an invention that came later, when minds on the ground saw a new chance. ICE was not a headline name. It had no golden record, no dramatic images. Most people today have never heard of it. But it was the first to fly through a comet's tail, the first to orbit a Lagrange point, the first to be revived by citizens rather than space agencies. Now it is one of the quiet objects drifting through the solar system, still in orbit, still whole, but invisible to the unaided eye. Somewhere out there, not too far from Earth in the scale of space, ICE circles the Sun. Its solar panels still face the light, but their current has nowhere to go. Its instruments are powered down. Its mission is long past. It is part of a group of machines that tell a story not just of exploration, but of persistence, of how even forgotten tools can carve a place in history. The dusty corpses of Mars missions that never phoned home. Mars, now familiar to scientists and engineers, was once a graveyard for early space ambitions. Long before rovers rolled across its surface and helicopters took flight, many spacecraft died quiet deaths trying just to make contact. They were the first wave. Most never called home. Some were lost in the blink of an eye. Others may have made it to the surface, only to fall silent before they could speak. The history of failed Mars missions goes back to the early days of space exploration. The Soviet Union was the first to try. In the 1960s and 1970s, they launched a series of probes under the Mars program. They were built with the technology of their time, large, heavy, and complex. But Mars is a hard target. Getting there is difficult. Landing is harder. Communicating afterward is the hardest part of all. Mars 1, launched in 1962, was one of the very first interplanetary missions. It flew past the Earth and left orbit successfully, but communication was lost after about 100 million kilometers. The probe kept flying, but it never sent back another signal. Engineers believed a leak in the gas lines used to control its orientation led to the failure. The spacecraft is still out there, silently circling the Sun. Mars 2 and Mars 3 were launched in 1971 with great hope. Each included an orbiter and a lander. Mars 2's lander was released too early during descent. It entered the Martian atmosphere at a steep angle and crashed onto the surface. No data was ever received. Mars 3's lander did touch down successfully. For a moment, it made history. It was the first spacecraft to soft land on Mars. But the moment was brief. The signal lasted only 14.5 seconds before going dead. The cause is unknown. It may have been a fierce dust storm, equipment failure, or both. For decades, no one knew exactly where the lander had come to rest. In 2013, a team of amateur researchers working with high-resolution Mars Reconnaissance Orbiter images believed they had spotted the remnants of Mars 3's lander. They identified several objects on the surface consistent with the parachute, heat shield, and the lander itself. But Mars 3's silence remains. It touched Mars and died in the same breath. Soviet attempts continued, but luck did not improve. Mars 4 and Mars 5 launched in 1973. Mars 4 missed orbit insertion and flew past the planet. Mars 5 did make orbit, but contact was lost after a few days. Mars 6 released a lander which transmitted data during descent until the moment of impact. It hit the ground and stopped responding. Mars 7's lander never even made it to the atmosphere. A failure in its release system caused it to drift past the planet. All these missions, launched with high hopes, ended in silence. Pieces of them may still be on or near Mars, invisible from Earth, preserved in dust. The United States also struggled. Before Viking, there was Mariner. Mariner 3 failed to escape Earth orbit due to a faulty shroud. Mariner 8 met the same fate, crashing into the Atlantic. Mariner 9 was successful and became the first spacecraft to orbit another planet, but it was not alone in its development cycle. The Mars Observer was another US mission, launched in 1992. It was designed to study the Martian surface, magnetic field, and climate. It carried advanced instruments and marked NASA's return to Mars after Viking. But just days before it was due to enter Mars orbit, it went silent. The likely cause was a fuel tank rupture during pressurization. Engineers listened for weeks, sending signals, waiting for any trace. Mars Observer was lost without ever reaching its target. It may have exploded, or it may still orbit the Sun, an unintended monument to how fragile interplanetary communication can be. In 1999, NASA launched the Mars Climate Orbiter. It was designed to relay communications for the Mars Polar Lander and gather atmospheric data. But its mission ended in a mistake. Two teams had used different units for calculations. One used metric, the other imperial. As a result, the orbiter entered Mars's atmosphere too low and burned up. The error was human, not technical. A mission undone by simple confusion. Later that year, the Mars Polar Lander followed. Its goal was to touch down near the planet's south pole and search for signs of water ice. It carried scientific instruments, including a small microphone to capture the first sounds from another world, but just before landing, it vanished. Investigations later suggested that the lander may have shut off its engines too early, mistaking vibrations for touchdown. It likely crashed into the ground at high speed. Two small probes attached to the Mars Polar Lander, called Deep Space 2, were also part of this mission. They were meant to punch into the surface and relay data from beneath. Neither sent a signal. These were experimental units, and their silence was not unexpected. Still, they marked yet another loss on a growing list. India's Mars Orbiter mission, launched in 2013, was a major achievement. It became the first Asian spacecraft to reach Mars orbit. But in 2022, contact was lost. Officials believe it ran out of fuel during a solar eclipse event, unable to maintain its orbit. These silent missions taught engineers hard lessons. Every lost signal was studied. Every crash was examined. Mars demanded precision. It punished overconfidence. Today's success stories like Curiosity, Perseverance, and Ingenuity stand on a foundation built by these earlier sacrifices. The Martian Dead, Beagle 2, Schiaparelli, and the Curse of Red Planet landings. Missions to the Red Planet have failed at an unusually high rate. Launches would go wrong, rockets would misfire, landers would vanish, and orbiters would never return a signal. The technical term is anomalous failure. But to the people working on these projects, it felt like Mars just didn't want to be touched. Two missions in particular came to represent this feeling. Beagle 2 was the first. It was named after the ship that carried Charles Darwin and was part of the European Space Agency's Mars Express mission. Mars Express would remain in orbit, while Beagle 2 would detach and descend to the surface. It was small and light, designed to land in the Isidis Planitia region, near the Martian equator. Its goal was to look for signs of past or present life. It carried a robotic arm, a sampling device, and several cameras. It even had a tiny microphone to record Martian sounds, something no mission had done before. Beagle 2 was Europe's first try at a Mars landing. It was also a source of national pride for the UK. Scientists, engineers, and the public followed its journey closely. But as Christmas 2003 approached, the mission entered a silent phase. Beagle 2 was supposed to touch down on December the 25th. Its first signal would have been the best holiday gift for the mission team. But no signal came. Ground stations listened. The Mars Express orbiter tried to contact it. NASA's orbiters joined the effort. Still, nothing. For over a decade, Beagle 2 remained a mystery. Had it burned up in the atmosphere? Had it crashed into a boulder field? Had its parachutes failed? There were no answers. Then, in January 2015, NASA's Mars Reconnaissance Orbiter, scanning the planet with its high-resolution camera, spotted something odd in Isidis Planitia, a small set of objects that didn't match the natural terrain. Image analysis revealed them to be parts of Beagle 2. There was the main body. There were pieces of its heat shield. And most remarkably, the lander itself appeared to be intact. But something was off. The lander was shaped like a clamshell with solar panels that folded out. It looked like only some of them had deployed. If the communications antenna was under one of the stuck panels, it would never have been able to send a signal. That seemed to be exactly what had happened. Beagle 2 had landed successfully. It had survived descent. It had done everything right, except finish opening. In the end, a simple mechanical failure had buried a historic success under 11 years of silence. It was a bittersweet discovery. Just over a decade after Beagle 2, a second story unfolded. This one belonged to Schiaparelli. Named after the 19th century astronomer who mapped Mars, it was part of the European Space Agency's ExoMars mission. The idea was to test landing technologies for a future rover. Schiaparelli was meant to be a demonstration lander. Its primary mission was to get to the surface safely, test sensors, and beam back descent data. It would also perform some short-term science after landing. It launched in March 2016 and travelled alongside the Trace Gas Orbiter, which would enter orbit to study gases in the Martian atmosphere. In October 2016, Schiaparelli separated from the orbiter and began its descent. It entered the atmosphere, deployed its parachute, and jettisoned its heat shield. Data from the descent was received for a short time, but contact was lost just before landing. The mission team quickly began looking through the telemetry. They found an odd pattern. The lander had misjudged its altitude. Because of a sensor issue, it thought it was below ground level, so it shut off its descent engines too early and ejected the parachute. With nothing to slow it, the lander fell freely and struck the surface at high speed. Images from the Mars Reconnaissance Orbiter later confirmed the crash. The dark stain on the Martian soil marked where Schiaparelli had hit. The wreckage was visible, along with parts of the parachute and heat shield. Like Beagle 2, it had come heartbreakingly close to working. All systems had functioned up to the final moments. Then a brief software confusion, and it was over. The idea of a Mars curse isn't scientific, but it stuck around because of stories like these. Before perseverance, curiosity, spirit, and opportunity, there was a long list of missions that never came home. Soviet landers like Mars 3 and Mars 6, US attempts like Mars Polar Lander, and European hopes like Beagle 2 and Schiaparelli. Mars is hard. Its thin atmosphere means parachutes don't work well. The terrain is rocky and uneven. Communications lag by minutes, and even now, every descent to its surface is a high-risk manoeuvre. Beagle 2 and Schiaparelli are still there, just beneath the surface dust, or lying exposed in sunlight, quiet reminders of human ambition and the limits of control. Each carries with it years of work, countless hours of engineering, and the hopes of entire teams. Today, they are joined by newer missions. Rovers roam the surface. Orbiters scan the planet. Helicopters fly short hops. But the path to that success was paved by these early sacrifices. Mars did not welcome visitors easily, but every lander that fell short made the path for the next one just a little more clear. Messenger, the first Mercury orbiter, now crushed in silence. Mercury is a place that barely feels real. It's the closest planet to the Sun, a scorched world of extremes. One side can reach 420 degrees Fahrenheit, while the other plunges far below freezing. It has no real atmosphere. It's small, cratered, and heavily battered by solar radiation. It reflects sunlight like a metal plate left in the desert, and for most of history, it was also largely unknown. Too hard to study from Earth, too close to the Sun for telescopes, too difficult to reach with spacecraft. Then came Messenger. Launched by NASA in 2004, Messenger was an acronym: Mercury Surface, Space Environment, Geochemistry, and Ranging. It was the first spacecraft ever to go into orbit around Mercury. Before that, the only visit had been a quick flyby by Mariner 10 in the 70s. Mariner had shown a strange world, but it had only mapped about 45% of the surface. After that, the planet went back to silence. It would take 3 decades before another mission returned. Getting to Mercury is harder than it seems. Most deep space missions aim outward. Mercury lies inward, close to the massive gravity of the Sun. To slow down enough to orbit the planet, a spacecraft must shed speed, lots of it. That takes time and clever trajectory design. Messenger took 7 years and 6 planetary flybys, 1 of Earth, 2 of Venus, and 3 of Mercury itself, before it could settle into orbit in March 2011. That long route was necessary to slowly break its speed using gravity assists, because traditional engines couldn't do the job alone. Once in orbit, Messenger circled the planet every 12 hours. Its suite of instruments scanned the surface, measured the magnetic field, studied the exosphere, and took pictures. The photos were stark and full of impact scars, but they also showed bright spots, strange hollows, and ancient ridges. Mercury turned out to be a far more geologically active body than anyone expected. Some parts of its surface had features that looked like they had formed relatively recently, in the last few million years. One of the surprises was ice. Mercury's poles are tilted almost perfectly upright, which means some crater floors near the poles never see sunlight. In those shadowed pockets, Messenger found radar-bright regions, consistent with water ice. The idea of ice on the closest planet to the Sun seemed impossible, but there it was, locked in eternal shade, protected from heat by geography alone. Messenger also helped solve an old puzzle: why Mercury was so dense. It has a massive iron core, much larger than expected for its size. One theory was that early in its life, a huge collision stripped off much of its crust, leaving behind a metal-rich world. Messenger's measurements supported this. It showed that Mercury's surface was low in volatile elements, things like potassium and sulfur, which suggested intense heat and violent history. Messenger also studied the environment around the planet. Mercury has a weak but active magnetic field. Messenger measured how solar wind particles interacted with that field, causing waves and disturbances. Unlike Earth's magnetosphere, Mercury's is constantly being pushed around by the Sun. It's chaotic and compressed. The spacecraft captured bursts of particles, fast-moving plasma, and magnetic reconnection events, tiny explosions in space that flip magnetic fields and fling charged particles at high speed. Over 4 years in orbit, Messenger completed more than 4,000 orbits. It sent back hundreds of thousands of images and an enormous volume of data. And then it began to run out of fuel. Without fuel, Messenger couldn't adjust its orbit. Mercury's gravity, plus the constant pressure from the Sun's radiation, slowly dragged the spacecraft lower. The team extended its life with clever maneuvers, even using helium, originally meant to pressurize its fuel tanks, to eke out the last adjustments. But by early 2015, it was clear. The end was coming. On April 30th, 2015, Messenger struck the surface of Mercury at a speed of over 8,700 miles per hour. It left a small crater somewhere in the northern hemisphere, near a ridge called Shakespeare Basin. No spacecraft has seen the crater. Messenger itself was the only one in Mercury orbit. The crash wasn't witnessed directly. The signal just stopped. It was a planned descent. The engineers and scientists knew exactly when and where it would hit. They even used its final days to do ultra-low passes, dipping within a few kilometers of the surface to get high-resolution scans. These last sweeps added detail to an already rich dataset. The crater it left behind may someday be imaged by a future mission. But for now, it remains a hidden mark, buried in the dust of an airless world. Messenger was the first mission to orbit Mercury. It made its discoveries alone, without a fleet of satellites or landers. It had no backup, no follow-up spacecraft watching from a distance. Its crash was the conclusion of a mission that had already lasted twice as long as planned. But once the last signal vanished, there was nothing left listening. No human eyes have ever seen Mercury up close. The planet is too hot, too near the Sun, too hard to visit. Even Messenger only glimpsed it through cameras. But it revealed a world of surprises, a dynamic, volatile and complex place shaped by forces we barely understand. Its surface is old, but not dead. Its magnetic field is weak, but alive. Its polar regions are frozen, but only in shadow. Now that Messenger is gone, there is nothing at Mercury. No spacecraft in orbit, no active mission on the surface, no signals coming back. Just a quiet, rotating planet scorched by sunlight. The only trace of the mission is a crater and the massive data set it left behind. A new mission, Bepi Colombo, is on its way, a joint effort by the European and Japanese space agencies. It will arrive in November of 2026. But until then, Mercury remains in silence. Dawn and the fading light between Ceres and Vesta. Dawn was launched on September the 27th, 2007, riding atop a Delta II rocket from Cape Canaveral. Most spacecraft are built with a single goal in mind, a planet, a moon, a comet. But Dawn's mission was to explore two worlds in the asteroid belt, Vesta and Ceres. These were not ordinary asteroids, they were large, complex and ancient. Each held clues to the early solar system. Dawn was designed to visit both, becoming the first spacecraft to orbit two extraterrestrial bodies in one mission. Vesta came first. Dawn arrived in July 2011 after nearly 4 years in flight. By that time, it had already made history just by getting there. It used ion propulsion, a technology that allows a spacecraft to move using a gentle but steady push of electrically charged particles. It's slow but efficient. Instead of burning through fuel in one big burst, it drifts along quietly, accelerating over months or even years. Ion engines gave Dawn the flexibility to leave orbit and go elsewhere, something conventional chemical propulsion couldn't manage. Vesta looked like a battered relic. It had a lopsided shape marked by one massive scar, a giant impact basin near its south pole called Rhea Silvia. This colossal crater is around 300 miles wide, nearly the full width of Vesta itself. The force of that impact likely ejected enough debris to seed smaller asteroids found in meteorite collections on Earth. Some scientists believe that chunks of Vesta have been landing on Earth for millions of years. Dawn mapped the surface, measured its composition, and recorded its shape with high precision. What it found was a world full of sharp ridges, ancient lava flows, and strange troughs. It was dry, rocky, and differentiated, meaning it had layers, like Earth. It had a crust, mantle, and core. That made it more like a tiny protoplanet than a simple asteroid. Vesta had once been on the path to becoming a full-fledged planet, but something stopped its growth early on. Studying it gave researchers a window into how rocky planets might have formed, and what can interrupt that process. Dawn stayed at Vesta for over a year, then slowly spiraled away. Its next stop would be Ceres, the largest object in the asteroid belt and the only dwarf planet in the inner solar system. Ceres is different from Vesta in nearly every way. It's round, with a smoother shape. It's darker, less dense, and full of water-bearing minerals. Dawn arrived there in March 2015. Once again, it slipped into orbit quietly and began to look down. As Dawn got closer, it revealed clusters of reflective areas inside craters. The most famous of these is in a crater called Okator. At first, no one was sure what they were. Ice? Salt? Reflections from surface crystals? Eventually, data pointed to the presence of sodium carbonate, a kind of salt that had leached up from within the dwarf planet. It meant there had once been liquid, possibly underground brine, and that even now, Ceres may be geologically active. Ceres didn't have the hard, rocky structure of Vesta. Its surface was soft in comparison. Dawn spotted domes, fractures, and cryovolcanoes, cold volcanoes that release water or mud instead of molten rock. One such dome, named Ahuna Mons, looked like a smooth, lonely mountain, rising over 3 miles above the surrounding terrain. It may be a sign of recent internal activity, suggesting that Ceres is not completely frozen and dead, but something more complex. Dawn orbited Ceres for years, changing its altitude several times to capture data at different resolutions. Its lowest orbit brought it within just 22 miles of the surface, close enough to make out individual boulders and subtle changes in terrain. It didn't carry a lander, but it created a map that future landers could use. Every crater, ridge, and basin was charted with care. Dawn relied on solar panels, and while Ceres is far from the Sun, the panels were large enough to keep it running. But another issue emerged. The hydrazine fuel that powered its orientation system was running out. Without hydrazine, the spacecraft couldn't point its antennas, cameras, or solar panels. It would lose contact and slowly drift. By late 2018, the end was clear. The team had pushed the spacecraft to its limits, using up the last reserves of fuel with careful planning. On October 31st, 2018, Dawn missed a scheduled communication session. It was no surprise. Engineers had been waiting for that silence. The next day, it missed another. Dawn was gone. It had powered down, unable to point its antenna. The mission was over. Dawn's body remains in orbit around Ceres. Unlike Messenger, it didn't crash. Instead, it continues circling quietly, a dead machine above a cold world. It was placed in a stable orbit, one that could last for decades, even centuries. NASA chose not to crash it into the surface to avoid any risk of contaminating an environment that might still hold traces of water or organic compounds. Few missions had traveled so far, changed orbits so drastically, or lingered so long at two completely different worlds. It showed that small bodies, asteroids, and dwarf planets are not just debris, but windows into the earliest days of the solar system. Ceres and Vesta are survivors, objects that avoided being consumed or flung out during planet formation. The mission bridged the gap between planetary science and asteroid science. Vesta, dry and rocky. Ceres, icy and soft. Two different evolutionary paths, both interrupted, both frozen in time, and now both charted by a single machine. Today, if you look at a high-resolution map of Ceres or Vesta, you are seeing Dawn's legacy. Every mountain, every crater, every strange patch of brightness. Those are pieces of a story that began long before Earth formed, and that might still hold secrets about how everything else came to be. Rosetta's sleep beside a comet, a poetic end. Rosetta was launched on March 2, 2004 from French Guiana. Its goal was to catch a comet, not just fly by it, not just snap photos from a distance, but to match orbits, fly alongside it, study it in detail, and eventually to land a probe on it. The target was Comet 67P/Churyumov-Gerasimenko, a dark, oddly shaped body of ice and dust looping through the solar system on a 6.5-year orbit around the Sun. When Rosetta launched, the comet wasn't even close. The chase would take more than a decade. To reach 67P, Rosetta needed help. It used gravity assist to gain speed and adjust course. Between 2004 and 2009, it flew by Earth 3 times and Mars once. Then, with no more planets to pull it along, it went to sleep. In June 2011, Rosetta was placed into hibernation. Its system shut down to preserve power as it drifted deeper into space. Only a timer kept it connected to the mission plan. For 31 months, the spacecraft said nothing. On January 20th, 2014, it woke up. A signal reached Earth 45 minutes later. Rosetta was alive. Its target, the comet, was still ahead. Over the next several months, Rosetta closed in, taking images that slowly revealed more about 67P. From far away, the comet looked like a tiny dot. As it grew larger, its shape became clearer and stranger. It was not spherical, but more like 2 lumpy lobes joined by a thinner neck. Some called it rubber duck-shaped. It was about 4 kilometers across, dark as charcoal, covered in craters, cliffs and pits. No one had seen a world like it up close. By August 2014, Rosetta entered orbit, becoming the first spacecraft to do so around a comet. The environment around the comet was changing constantly, as gases and particles vented from its surface in long, wispy jets. Navigating near it was not easy. But Rosetta began its work, taking detailed images, mapping the terrain, studying the gases in the coma, and analysing how sunlight affected the comet's surface and structure. 3 months later, on November the 12th, 2014, came the next step, the landing of Philae. It was a small probe attached to Rosetta's side, designed to detach, fall gently, and land on the surface. It carried scientific instruments and drills, but no propulsion system. It relied on cold gas thrusters, harpoons, and ice screws to anchor itself after touchdown. But things didn't go as planned. Philae detached successfully and descended slowly. It made contact with the surface, but the harpoons failed to fire. Without a firm anchor, the lander bounced. For nearly 2 hours, it flew across the comet in a long arc, then hit again, bounced once more, and finally came to rest in a shadowy crack or hollow, partly tipped over. Sunlight was blocked, its solar panels couldn't charge, it sent back data for about 60 hours, then went silent. Still, during that short time, it managed to transmit measurements of the surface, the subsurface, and the complex chemical makeup of the comet's material. Rosetta continued alone. For the next 2 years, it circled, moved away, came back, changed altitudes, and watched the comet change as it approached the Sun. As the heat increased, 67P became more active, shedding more gas and dust. The jets grew stronger. The surface showed signs of collapse and movement. Pits formed. Ice became exposed. Rosetta watched all of it. Then slowly, the comet began moving away from the Sun again. The activity dropped. The environment became calmer, but sunlight was also fading. Rosetta too depended on solar panels. Its power levels were dropping. Engineers knew the end was coming. There was no plan to leave Rosetta in orbit. Comet gravity is too weak and irregular to allow for a long-term stable orbit. It would either crash into the surface uncontrollably or drift away. Instead, the mission team made a decision. Rosetta would descend one last time, slowly, with care. The descent would be controlled, gradual, and deliberate. Rosetta would become part of the comet it had followed for years. The final descent took place on September 30th, 2016. It was a gentle spiral downward. Rosetta kept its instruments active during the fall. It continued taking images, sampling gases, and collecting data until the very last moment. Its final images were its closest, showing surface dust grains, cracked terrain and boulders just a metre across. Its last readings came from just metres above the surface. Then, as expected, it lost contact. The mission had ended. Rosetta had joined the comet. It wasn't a crash in the traditional sense. The impact speed was less than a walking pace. There was no explosion, no debris, just a quiet end on a quiet world. Because the comet was still venting gas, though gently, Rosetta's body would likely be buried or covered with dust over time. It may be there still, hidden in shadow, resting beside the world it had studied so closely. No other spacecraft had ended this way. Even now, researchers continue analysing Rosetta's data. It changed the way scientists understand comets. The dust grains it sampled, the chemical compounds it detected, the way light and heat altered the surface. These were things no one had seen so clearly before. Comet 67P continues on its journey through the solar system, circling the Sun, looping out beyond Mars, and then back in. Somewhere on that uneven surface is a lander, tipped into shadow, and somewhere nearby, slowly decaying, is the orbiter that brought it there. Hayabusa's ashes in the atmosphere. When Hayabusa launched in May 2003, it carried hopes that a small spacecraft from Earth could chase down a fast-moving object in deep space, land on it, collect samples, and return those samples safely to Earth. This had never been done before. The spacecraft developed by JAXA, Japan's space agency, was light and compact. It carried ion engines, small sampling equipment, and a tiny lander named Minerva. It was aimed at a near-Earth asteroid called Itokawa, a small, stony body shaped like a potato and just over 500 meters long. Hayabusa had to travel over 2 billion kilometers to intercept the asteroid, which it reached in mid-2005. Along the way, the spacecraft suffered technical failures. Its solar panels delivered less power than expected due to damage, and one of its reaction wheels, used for orientation, stopped working. Still, Hayabusa pressed on. When it finally arrived at Itokawa, it became the first spacecraft to both orbit and attempt to land on such a small body. Instead of being a smooth, solid rock, Itokawa was a loose pile of rubble, grains, pebbles, boulders, and voids, all held together by gravity. This complicated things. The lander Minerva was deployed, but due to a misjudged separation maneuver, it drifted off into space and was lost. It never touched the asteroid's surface. Then came the sampling. Hayabusa attempted to descend, contact the surface, fire a small projectile into the ground, and collect some of the debris kicked up. Its first attempt failed. No projectile fired. A second attempt was made under unclear conditions. The onboard systems glitched and telemetry was partial. It was unclear whether a sample had been collected at all. Meanwhile, the spacecraft had taken damage and more of its reaction wheels had failed. Then, as it prepared to depart from Itokawa, a fuel leak caused its attitude to drift. Communication was lost for weeks. Many feared it was gone, but Hayabusa came back. The team slowly re-established contact and regained limited control. Despite its many problems, the spacecraft managed to make the long journey home. It limped back using its ion engines, correcting course little by little. When it neared Earth in June 2010, the mission reached its most dramatic moment. The spacecraft released its sample return capsule aimed at Australia's Venera test range. The capsule plunged into the atmosphere, trailing a brilliant fireball, slowed by a heat shield and a parachute, and finally landed in the desert. Hayabusa itself did not survive the re-entry. It disintegrated in the atmosphere, burning up like a shooting star. But the capsule was recovered intact. When scientists opened it, they were cautious. For a while, it seemed possible it might be empty. But careful inspection revealed tiny grains, some less than a millimetre across, trapped inside. They were from Itokawa. They were real. Hayabusa, despite all its issues, had succeeded. It was the first mission to bring back samples from an asteroid. But this was not the end of Hayabusa's story. Before launch, engineers had built duplicate hardware, spare parts, backup modules, and even nearly complete copies of the spacecraft. This is common in space missions, especially for new or untested systems. These engineering models, or ground spares, are built for testing, troubleshooting, and training. In Hayabusa's case, one of these nearly complete models became the basis for a new mission. That mission would become Hayabusa 2. Using what they had learned from the first Hayabusa, the engineers made improvements. Hayabusa 2 had upgraded thrusters, more robust sampling tools, improved navigation, and a larger set of deployable instruments. It launched in 2014, bound for a different asteroid, Ryugu. Like its predecessor, it used ion engines and gravity assists. In 2018, it arrived at Ryugu and began detailed mapping. This time, the mission went more smoothly. Hayabusa 2 deployed multiple landers, including Minerva, 2 rovers that hopped across the surface. It successfully collected 2 samples from different sites on the asteroid. For one of them, it even fired a small explosive device to expose subsurface material before collecting it. In 2020, Hayabusa 2 returned to Earth. Like the first mission, it released a sample return capsule over Australia. This time, however, Hayabusa 2 had more fuel and functioning systems. Rather than end its mission, it performed a flyby and continued into space. It now travels toward a new target, a small asteroid named 1998 KY26, which it will reach in the 2030s. Back on Earth, the capsule was opened. Inside were over 5 grams of material, far more than Hayabusa 1 had returned. These grains, pebbles and dust from Ryugu now sit in labs, being studied for clues about the early solar system, organic molecules and water. And so, while the original Hayabusa ended as ashes in the upper atmosphere, its clone, rebuilt, revised and renamed, drifts onward. Hayabusa 2 is a continuation not only in name, but in hardware and in spirit. The spares of the original became the tools of the future. It's rare for hardware to have a second life. Most missions, once launched, are the only version of themselves. Hayabusa's parts were different. Some were left behind. The sample capsule rests on Earth. The spacecraft itself is gone. But others, the engineering models, the backup frames, the tools and modules, were built again and given purpose again. As Hayabusa 2 travels toward its second asteroid, it does so with the legacy of that first attempt. A mission once called a failure, now remembered as a success. And in the silence of deep space, far from Earth, the clone carries forward what the original could not finish alone. What did Genesis leave behind? Genesis was launched by NASA in August 2001 with one clear goal: to collect particles of the solar wind and bring them back to Earth. To do this, Genesis needed to travel far beyond Earth's atmosphere, well outside any contamination from our planet, and wait, motionless, for the tiniest pieces of the Sun to drift into specially designed collector panels. The mission was a slow ballet of stability. It travelled to the L1 Lagrange point where gravitational forces from Earth and the Sun balance out, allowing a spacecraft to remain in a kind of gravitational neutral zone. Genesis stayed at L1 for over 2 years, from late 2001 through 2004, collecting particles. It used a series of ultra-pure collector arrays made from silicon, gold, sapphire and diamond-like materials laid out in fragile panels. These panels caught and trapped ions from the solar wind. The solar wind is incredibly sparse, but given enough time, even those few particles can build up a measurable sample. And the purity of the materials used ensured that when the particles did land, scientists could tell exactly what they were made of. Once the panels had done their job, Genesis began its journey home. The sample return capsule, packed with the precious collector arrays, was scheduled to re-enter Earth's atmosphere in September 2004. This was supposed to be the smooth finale. The plan was carefully timed. A parachute would deploy. A helicopter would catch the capsule mid-air before it touched the ground. This kind of mid-air capture had been practiced before. The capsule was not built to survive a hard landing. If it hit the Earth at full speed, the panels would shatter. The capsule entered the atmosphere just as planned, but the parachute never deployed. A sensor designed to detect deceleration and trigger the chute had been installed backward. Because of this, the system thought the capsule was still in space. It fell, rapidly accelerating down through the sky and into the Utah desert. When it hit the ground, it was traveling at nearly 200 miles per hour. The impact destroyed most of the internal structure. The capsule tore apart. The fragile collector panels shattered into thousands of pieces. Dust, glass and soil sprayed across the desert floor. What had been a gentle science mission turned into a disaster zone, but even in disaster, some pieces remained. Recovery teams moved quickly. They set up clean rooms in the field. They searched through the debris, not just for large fragments, but for powder, chips, dust, even contamination that might still hold a trace of the solar wind. Some of the collector material, though broken, was still usable. Not all science was lost. Over time, scientists were able to analyze these fragments. They developed new techniques to clean and isolate particles from the wreckage. It wasn't ideal, but the data started to come in. Genesis had managed to capture some of the most pristine solar wind samples ever studied. The mission confirmed key details about the Sun's composition and gave new insight into the differences between the Sun and the planets that formed around it. For example, the solar wind contained different levels of oxygen and nitrogen isotopes than those found on Earth. This suggested that the material that formed the planets had already undergone some kind of fractionation, some process that made it different from the raw material of the Sun. In that sense, Genesis was a partial success, but its crash also left other traces, ones that are harder to measure. Some debris from the capsule scattered far and wide. There were small pieces of heat shield, wiring, and broken panel fragments that could not all be recovered. Some of these pieces may have remained in the Utah desert, buried under layers of sand and dust. Others, though, are rumored to have drifted upward. Genesis did not separate cleanly from the spacecraft bus before re-entry. The capsule came down, but the main spacecraft, which had once housed the power and communication systems, was redirected towards solar orbit. Its path after the capsule separation took it back into space. Though it no longer had a mission and most of its systems had shut down, it was not destroyed. That bus, silent, dead and unpowered, continues to orbit the Sun. It drifts, locked in a lonely solar path similar to Earth's, but no longer guided or monitored. Its existence isn't widely tracked anymore, but models of its trajectory suggest it could remain in solar orbit for hundreds of years, maybe longer. So, Genesis left behind two kinds of ghosts. One is on Earth, the crater in the Utah desert, the twisted remains of its capsule, and the stories told by engineers who watched their careful plan collapse in an instant. The other is in space, The drifting spacecraft bus, once full of instruments and control systems, now just a dead object floating near the inner solar system. These leftovers aren't part of Genesis's main scientific legacy, but they are part of its footprint. Most people think of failed missions as simply data lost or goals not met, but they also leave physical evidence. Objects that hit the Earth or drift in orbit don't just vanish. They become part of the untracked archive of space activity, the hardware that didn't quite work as intended, but still exists somewhere. Genesis's crash led to changes in parachute design, sensor redundancy, and the inspection processes used for capsule recovery. Its failure, studied closely, may have helped save later missions from a similar fate. But for some, it's the emotional imprint that lingers. Scientists spent years planning Genesis. The materials used in its collector arrays were handmade in labs and handled with extreme care. To see those delicate surfaces shattered and mixed with dirt was a loss. It felt personal. Some engineers cried, others simply walked away from the capsule, stunned. Yet the data that did survive became precious. Every ion, every atom became more valuable because of the accident. Scientists treated each recovered particle as something rescued rather than delivered. In the lab, researchers still study those tiny fragments today. Above Earth, the original bus of Genesis continues to orbit the Sun. It is still out there somewhere in the solar wind it was once meant to sample, circling the star that gave it its name, Earth's graveyard orbit, where defunct satellites go to die. Thousands of satellites orbit the Earth. Some still work, sending back data or relaying signals. Others, though, have gone silent. Their fuel ran out, their electronics failed, their missions ended. Many remain up there, drifting in silence. But not all are left to fall wherever they may. Some are carefully guided to a place few people know exists, a place sometimes called the graveyard orbit. The graveyard orbit is not a single location, it's a zone, a band of space above Earth, sitting just a little higher than the geostationary belt. This region, roughly 300 kilometers above the standard geostationary orbit, is where dead satellites are pushed when their work is done. Geostationary orbit itself is special. Satellites here circle the Earth at about 35,786 kilometers above the equator. At that altitude, their speed matches Earth's rotation. From the ground, they seem to hang in place. This makes them perfect for communications, weather forecasting and television broadcasts. A dish on Earth can point to the same satellite all day, every day, without needing to move. But space in the geostationary belt is limited. Each satellite has to stay in its assigned slot, so signals don't interfere. The closer they are to each other, the more crowded the belt becomes. And with more than 400 satellites already stationed there, and more being launched every year, managing traffic is no small task. That's where the graveyard orbit comes in. When a satellite in geostationary orbit reaches the end of its operational life, the responsible agency or company can send it upward, out of the active belt and into the higher, quieter zone. The satellite uses its last reserves of fuel to fire small thrusters, lifting itself just a few hundred kilometers higher. Once there, it's out of the way. It won't drift back down quickly, and it won't interfere with working satellites. This final maneuver is a last act of service. Not all satellites make it to the graveyard. Some fail before this final move can be done. If they lose contact too early or run out of fuel unexpectedly, they might stay stuck in the main orbit, turning slowly, possibly tumbling, no longer able to hold position. These abandoned satellites become space debris. But when things go as planned, the graveyard orbit becomes their quiet resting place. The International Telecommunication Union and other space agencies have set guidelines for this process. Operators are advised to boost satellites at least 300 kilometers above the geostationary ring. They must also vent remaining fuel to avoid explosions. Batteries are discharged. Moving parts are locked. Antennas are turned off. The satellite is, in every sense, powered down. Then it is left alone. In this graveyard orbit, hundreds of satellites now drift. Many have been there for decades. They are cold, inert, and lifeless. Some of them are relics from the early days of satellite communication. Others carried weather sensors or data relays. Now they serve no purpose except to stay out of the way. Unlike spacecraft sent toward the outer planets or interstellar space, these satellites remain tethered to Earth. They move in large, circular paths, always above the equator. But because they are no longer active, their orbits can slowly shift. Over time, slight pulls from the Sun, the Moon, and even the uneven mass of Earth itself can cause them to drift. Some begin to wobble. Others rotate unpredictably. But without fuel or functioning gyroscopes, they cannot correct themselves. Some are logged in databases, especially if they belong to major governments or commercial networks. But others, especially older or foreign satellites, are no longer watched. They become part of the hidden backdrop of space, known only in theory, not in detail. It is possible, in rare cases, that collisions could happen in the graveyard orbit. While the risk is low, it's not zero. With hundreds of objects already there and more arriving every year, the graveyard itself is becoming more crowded. Fortunately, satellites in this orbit move slowly relative to each other, so the chances of high-speed impacts are lower than in lower orbits. But if a collision did occur, it could create debris that spreads into other paths. Still, compared to the lower Earth orbits, like those used by Earth-observing satellites or space stations, the graveyard is a more stable, predictable zone. It is far from the atmosphere. There is no drag to slow objects down, and since no active missions operate at that altitude, there are fewer dangers of interference. Some of the satellites in this graveyard were famous once. Names like GOES, Intelsat or Eutelsat might appear in old news stories or technical reports. These were workhorses of communication, linking continents or providing real-time weather data. Others were military in nature, used for surveillance, tracking, or secure communication. Now they are silent shells. Their solar arrays, once tracking the Sun, now float without guidance. Paint peels, insulation wears down. Micrometeoroids may scar their surfaces. In a way, they are aging, just not in the way things age on Earth. There is no air, no weather, but time still leaves marks. There is no plan to bring them back. The graveyard orbit is too high for recovery. No shuttle or cargo mission has ever reached it. And since these satellites were never meant to return, they carry no engines or parachutes for re-entry. They will remain there for centuries, perhaps millennia. The graveyard orbit is a reminder of how long our presence in space lasts. Long after a mission ends, the physical craft remains. It stays locked in orbit, obeying the rules of physics, but no longer tied to human needs. Other orbits have their own kinds of graveyards. In low Earth orbit, dead satellites sometimes burn up in the atmosphere. Some are deliberately deorbited, sent to fall, and incinerate over oceans. But in the high altitudes of geostationary orbit, there is no easy return. The safest choice is to move upward, just far enough to avoid becoming a threat, and leave the satellite there. Every launch to geostationary orbit now includes end-of-life planning. Engineers design spacecraft with this last step in mind. They calculate the fuel needed for the final push to the graveyard. They build systems that can shut down safely, and they log the satellite's final position so future missions can steer clear. It is a kind of space etiquette, a rule agreed upon, not by law, but by necessity. The graveyard orbit helps keep the geostationary belt clean and usable. It is the silent solution to a long-term problem. From the ground, we cannot see these dead satellites. They are too far away. But if you could stand above the equator, high enough to look down on Earth and the geostationary ring, you would see a crowd. Hundreds of points, some alive, others long dead. And just above them, a ring of shadows, the graveyard where satellites go to rest. The imprint on Titan, Huygens' lonesome rest on an alien moon. On January 14, 2005, a small spacecraft parachuted through the thick, golden clouds of Saturn's largest moon. It moved slowly, steadily, drifting downward for hours. Beneath it was a world no one had ever seen up close. And as it dropped through the haze, the spacecraft took pictures, measured temperatures, and listened to the wind. Then it touched down. It became the first and only visitor to the surface of Titan. That spacecraft was Huygens. The Huygens probe was a part of the Cassini-Huygens mission, a collaboration between NASA, the European Space Agency, and the Italian Space Agency. Cassini was the larger piece, an orbiter that would circle Saturn for more than a decade. Huygens was much smaller. It was built to ride along, detach at the right moment, and fall to Titan, carrying instruments to study the strange, distant moon. Titan had been a mystery for a long time. Early images showed it wrapped in an orange shroud, hiding its surface from view. Astronomers knew it was cold. They knew it had a thick atmosphere, thicker than Earth's. Some even suspected that lakes or seas might exist there, not of water, but of liquid methane or ethane. The air was too cold and dense for water to flow, but other chemicals, usually gases on Earth, could form liquid on Titan. As Huygens descended, it passed through this thick alien air. For 2.5 hours, it slowly floated downward. Its parachutes opened in stages. Instruments turned on. The probe captured the first photos ever taken from within Titan's atmosphere. One of the most striking showed a vast, hilly landscape with dark branching lines like riverbeds. Another showed a smooth, rock-strewn surface, as if it had landed beside a dry stream. It sampled the atmosphere and found nitrogen as the main gas, just like Earth. But unlike Earth, there was also methane, and it behaved strangely. Some scientists had wondered if Huygens would splash down in a liquid sea. That didn't happen. Instead, it landed on solid ground, something like wet sand. For a short time after it touched down, Huygens kept sending data. The surface was around -179 degrees Celsius, cold enough to freeze most things solid. The rocks scattered around the lander weren't rock at all. They were likely made of water ice, as hard as stone in that deep cold. The dark material coating them might have been a kind of organic soot, particles made from methane and sunlight, drifting down like snow over millions of years. The probe survived for a little more than an hour on the surface. Then its batteries ran out. Its job was to land, work for a brief time, and then go silent. And that's exactly what it did. Now, Huygens sits alone on Titan. It is the only spacecraft ever to land there. No one has visited since. It rests somewhere near the moon's equator, surrounded by a frozen landscape shaped by chemistry we don't fully understand. Rain may fall there. Methane rain, falling from hydrocarbon clouds. Over time, it might form streams, carve gullies, or pool into dark lakes. Wind may blow fine particles across the land, slowly covering the probe with a thin film. But for now, and for the foreseeable future, it remains untouched. For the first time, humans landed on a place far beyond Mars. They dropped a small piece of technology onto an icy moon with alien skies. That moment, brief as it was, gave us a glimpse into a world that had only been imagined before. Titan is a unique place in the solar system. It is the only moon with a thick atmosphere. Its surface shows signs of erosion, of seasonal changes, of liquid flows. Some scientists even suggest that Titan might, under the right conditions, support a very different kind of life. Life not based on water, but on methane or ethane. Huygens didn't find life. It wasn't built to. But it did prove that Titan is more than just a cold rock. It is a world with weather, with chemistry, with change. Huygens is likely still in good shape. The extreme cold on Titan can preserve materials for a long time. There is no sunlight strong enough to damage its electronics, no animals to disturb it, no rust or decay in the way we see on Earth. The only changes would come slowly, from temperature shifts, wind-blown particles, or perhaps the slow fall of chemical haze from the sky. The probe's final resting place is not fully known. We know the general area where it landed, but no orbiter has yet captured a clear image of the lander itself. Cassini flew by many times after the landing, but Titan's thick atmosphere and surface haze make it hard to see details. One day, a future mission might find it, either by sight or by landing nearby. For now, though, it remains a lonely monument, a piece of Earth technology sitting silently on the surface of a cold alien world, waiting in the dark. Even the way it got there was unique. It had no engines of its own. It hitched a ride with Cassini, detached at the right moment, and coasted for weeks before entering Titan's atmosphere. It depended on careful planning, precise timing, and years of coordination. And all for a mission that lasted just a few hours. Still, those few hours reshaped how we think about the outer solar system. They gave scientists real data to study. They confirmed theories about Titan's surface and raised new questions. What kinds of materials lie below the frozen crust? Could complex molecules form there? Might Titan be home to something we've never imagined? Future missions to Titan are being planned. One of the most ambitious is a drone-like rotorcraft called Dragonfly, which could fly from place to place, studying the Moon's chemistry in greater detail. If it succeeds, it will expand on the legacy of Huygens, but it will not replace it. Huygens was the first, the Pathfinder, the quiet visitor that left behind a tiny imprint in the frozen soil of an alien moon. Long dead, but not forgotten. The legacy of early ESA missions. In the beginning, space was dominated by two giants, the United States and the Soviet Union. Their rockets launched the first satellites, the first humans, and the first probes to leave Earth orbit. But in the 1980s, another player began to step into the deep space arena. Europe, through the European Space Agency, started launching its own missions, not just satellites or Earth-observing craft, but probes that would journey far beyond our atmosphere. Giotto was one of the earliest and most ambitious deep space missions flown by ESA. Launched in 1985, it was designed to study Halley's Comet, which was making one of its rare appearances in the inner solar system. This was Europe's first mission to leave Earth orbit with the goal of encountering a celestial body beyond the Moon. Giotto was small, shaped like a squat cylinder, with a dish antenna pointed back at Earth. Its instruments were packed into a sturdy frame, and the front was covered by a protective shield, because approaching a comet wasn't just a photo opportunity. Comets release clouds of dust and gas as they near the Sun. Travelling into one of those clouds meant risk, especially at high speed. As Halley's Comet sped through the inner solar system in 1986, Giotto made its closest approach on March 13th. It came within 596 kilometres of the nucleus, close enough to send back images and measurements, but also close enough to take a beating. One piece of comet dust struck the spacecraft hard enough to knock it spinning. The camera was damaged, but it kept sending data. Giotto gave the world its first clear image of a comet nucleus. It was dark, oddly shaped, and very different from what many had imagined. Instead of a bright, icy ball, Halley's nucleus was a black, rugged object with jets of gas blasting from its surface. It confirmed that cometary bodies were made of a mix of ice, rock, and organic compounds. After that close pass, Giotto was thought to be finished. Its camera was out of commission, and the spacecraft had spun out of alignment. But engineers managed to regain control. and instead of letting the spacecraft drift away into obscurity, ESR planned a follow-up. Years later, in 1992, Giotto made a second comet flyby, this time of Comet Grigg-Skellerup. Since then, it has remained in solar orbit. Another early ESA mission was Ulysses, launched in 1990. Though it was a collaboration with NASA, its operations were managed largely by Europe. Ulysses was built to study the Sun, not by looking at it directly, but by flying over its poles. To do this, the spacecraft had to take a long and strange route, using Jupiter's gravity to slingshot itself out of the plane of the solar system. Once, in its final orbit, Ulysses circled the Sun at a steep angle, passing over the north and south poles. It carried instruments to measure the solar wind, magnetic fields, and cosmic particles. It operated far longer than expected, more than 18 years in total, before finally losing power in 2009. Now it is another silent traveller, drifting on a unique path far from the plane where most planets orbit. There were other missions too. The Infrared Space Observatory, launched in 1995, did not travel as far, but it left its mark. Herschel and Planck followed years later, giving Europe a strong presence in space-based astronomy. These observatories didn't explore planets or comets, but instead looked at the universe itself, its cold dust, distant galaxies, and the faint glow of the Big Bang. SMART 1, launched in 2003, was a testbed for solar electric propulsion. It went to the Moon, circled it for months, then was deliberately crashed. It showed that European-built spacecraft could reach beyond Earth and perform long-term science. It paved the way for more advanced missions. One of the most iconic of these was Rosetta. Both Giotto and Rosetta were separated by decades, but they were linked by shared goals, shared risks, and by a European desire to explore not just from orbit, but from up close. The early ESA missions were often smaller, sometimes built on tighter budgets and focused on specific scientific goals. But they were ambitious in their own way. They marked Europe's shift from launching weather satellites and science payloads to flying deep into the solar system. Occasionally, mission control might point a dish at the sky, hoping to catch a faint signal. In rare cases, it has happened. In 2008, ESR tracked Giotto again for a short time, confirming it was still tumbling through space. But the spacecraft did not respond. The silence confirmed what was already known. It was there, but it had nothing more to say. In time, new missions will follow. Europe continues to build spacecraft that reach far beyond Earth, like the Jupiter Icy Moons Explorer, launched to explore the moons of Jupiter. But the first steps were taken by small, simple probes. They proved it could be done. They earned their place in the silent fleet that now drifts between the stars. Deep impacts, broken eye, and the debris it left behind. NASA's Deep Impact Probe travelled over 130 million kilometres to reach Comet Tempel 1. When it arrived, it released a copper-filled impactor, essentially a bullet, and steered it directly into the comet's surface at over 10 kilometres per second. The resulting collision kicked up a cloud of dust and gas that glowed in sunlight, forming a temporary halo around the comet. For the first time, scientists were able to see inside a comet by forcefully opening it up. The mission had two main parts: the flyby spacecraft and the impactor. The flyby craft carried cameras, sensors, and a high-gain antenna. It watched from a safe distance, while the impactor, about the size of a small desk, took the plunge. The impactor itself had a simple goal: slam into the surface, survive long enough to send back close-up images, and then be obliterated. It performed exactly as planned. In its final moments, it took detailed pictures of the comet's surface, revealing a rough, shadowy terrain, pocked with ridges and slopes. Then the images stopped. A bright flash followed, captured by the flyby craft, marking the instant the impactor disappeared into a burst of ice, dust, and vapour. The flyby craft trained its instruments on the plume, capturing data on the dust particles, gas composition, and light patterns. Scientists learned that the interior of the comet was made of fine, powdery material, with traces of water, carbon dioxide, and complex organics. These were the raw ingredients of the solar system. The hope was that by studying this comet, scientists could better understand what the early solar system was made of and how life might have formed. But the impact had another consequence. It left behind a crater that was never seen in detail by the Deep Impact spacecraft. The cloud of debris was so dense and the flyby time so short that the spacecraft couldn't see through it to the hole it had just made. For a while, no one knew exactly what the aftermath looked like. Years later, in 2011, NASA's Stardust Next spacecraft flew by Comet Tempel 1 again. It spotted a shallow depression where the impactor had hit. The crater was about 150 meters wide and 20 meters deep, less dramatic than some had expected, but still clearly there. The wound in the comet's surface, while soft-edged, marked the place where humanity had reached out with a deliberate hand and reshaped a celestial body. After the main event, the Deep Impact flyby spacecraft remained functional. Instead of retiring it, NASA gave it more work. The spacecraft still had fuel, a working camera, and the ability to change its course. It was reprogrammed for a new mission, EPOXI, a combination of two science efforts, studying extrasolar planets and revisiting another comet. In 2010, Deep Impact encountered Comet Hartley 2, a smaller, more active body with jets spewing out carbon dioxide like a miniature engine. The images showed a peanut-shaped comet with one end covered in icy particles and the other end relatively quiet. It was the first detailed look at a small, hyperactive comet. Designed originally for a short mission, it had now been operating for years longer than planned. The spacecraft's systems were growing less reliable. In August 2013, contact was lost. The last signal received from Deep Impact showed that it had entered an error state. Engineers tried to re-establish communications, sending commands and scanning frequencies, but there was no response. Later investigation suggested that a timing error in the onboard computer caused it to lose track of its orientation. Without knowing where Earth or the Sun was, the spacecraft couldn't point its antenna or solar panels. It likely ran out of power and went silent. The debris cloud from its impact on Tempel 1 is still somewhere out there, stretched thin by solar radiation and pulled gently by the comet's weak gravity. Some of it may have settled back onto the surface. Other bits may have been carried away by the comet's own jets during later orbits. That cloud, once glowing and chaotic, is now part of the comet's long, dusty history. Most spacecraft pass by their targets, take measurements, and leave no trace. Deep Impact punched a hole in a comet and left behind evidence of its visit. It created data not just by watching, but by doing. If the impactor had missed or hit a rock too hard to penetrate, the mission might have failed. But it didn't, and the result was a new way to learn about small bodies in the solar system, by breaking into them. The impactor was destroyed, but the flyby spacecraft is still up there. It's now in a heliocentric orbit, circling the Sun once every 1.5 years. Without power or control, it can no longer adjust its path, but its orbit is stable. In a sense, Deep Impact's final years mirrored its name. The spacecraft's broken eye, the failed camera and the loss of control came only after years of hard work and high-risk success. Its demise was quiet, unceremonious, but what it accomplished had lasting effects. The crater on Tempel 1 remains as a sign of human curiosity, scratched onto the surface of a drifting icy relic. Phobos Grunt and the dreams of Russian Mars exploration. In the quiet hours of a November night in 2011, a Russian rocket climbed into the sky carrying with it a mission meant to revive a nation's legacy in deep space exploration. The spacecraft was called Phobos Grunt, a complex and ambitious probe named after its destination, Phobos, the larger and closer of Mars's two small moons. The word grunt means soil in Russian, reflecting the mission's most ambitious goal: to bring back a sample of Phobos's surface to Earth. It would have been Russia's first interplanetary sample return mission. If successful, it would have been a defining moment, placing Russia back in the lead of Mars exploration, decades after the glory days of the Soviet space program. Phobos Grunt was launched atop a Zenit 2 SB rocket from the Baikonur Cosmodrome in Kazakhstan. The launch itself went as planned, and the spacecraft successfully entered low Earth orbit. The upper stage, known as the Frigate Propulsion Module, was then supposed to ignite and send the spacecraft on a trajectory toward Mars. It never did. The spacecraft remained stranded in Earth orbit. Mission controllers tried repeatedly to send commands to wake the upper stage or alter the probe's course. But no response came. As hours turned into days and then weeks, the reality of the situation settled in. The spacecraft had power, its solar panels had deployed, and it was alive in a technical sense. But it was going nowhere. Russia's bold attempt to return to Mars had failed just one step off the ground. Engineers never fully confirmed the root cause in detail, but there were several likely suspects. One theory pointed to faults in the onboard software, possibly caused by radiation hitting sensitive chips. Others cited hurried development cycles, political pressure, and aging hardware infrastructure. The failure was a psychological blow to Russia's space community. Phobos Grunt was supposed to be a sign that Russia could once again carry out complex missions beyond Earth orbit. Since the collapse of the Soviet Union, Russia had struggled to fund and maintain interplanetary programs. Most of its space efforts had focused on low Earth orbit, such as the ISS and Earth observation satellites. Phobos Grunt was supposed to change that. It was not just a Russian project either. The mission also carried a small Chinese spacecraft called Yinghuo-1, China's first Mars probe. Yinghuo-1 was to separate from Phobos Grunt after arrival and orbit Mars independently, gathering data on its ionosphere and magnetic field. For China, this was a stepping stone into deep space, marking its first effort at reaching the Red Planet. That ambition fell with Phobos Grunt as well. Yinghuo-1 remained trapped aboard the stranded spacecraft. Also on board were small biological experiments, including microbial organisms, seeds, and even tiny crustaceans. These were part of a study to see how life might survive long-duration space travel. But like the spacecraft carrying them, they never left Earth's immediate grasp. For weeks, space agencies tracked the orbiting shell of Phobos Grunt. It circled the Earth again and again, slowly losing altitude as atmospheric drag began to pull it down. On January 15, 2012, after 2 months aloft, the spacecraft re-entered Earth's atmosphere over the Pacific Ocean. Most of it burned up during re-entry, though some debris may have splashed into the sea. This wasn't the first time Russia, or the Soviet Union before it, had aimed for Phobos. In 1988, the USSR launched 2 spacecraft, Phobos 1 and Phobos 2. Both were part of an earlier mission to study the Martian moon. Phobos 1 failed en route due to a software command error. Phobos 2 made it to Mars and even sent back some data and images. But just as it was preparing to release landers to the surface of Phobos, contact was lost. Those earlier failures haunted the design and planning of Phobos Grunt. Great effort was made to avoid repeating the past. And yet, the result was strikingly similar: loss of control, mission termination, and no science returned. Phobos Grunt was a modern mission designed in an era of increasing global collaboration. While past Soviet missions were largely isolated, Phobos Grunt involved partnerships and international payloads. It was meant to show Russia could still operate at the frontier of planetary science. Instead, it became a cautionary tale. Some pieces of it, the largest that survived atmospheric entry, might still lie at the bottom of the ocean. But like many failed missions, it also left less visible debris, scars on program confidence, questions about funding, and a pause in Russia's planetary exploration efforts. Phobos Grunt carried the hopes of engineers who had worked through the lean years after the fall of the Soviet Union, many of whom had waited decades for such a mission to become real. It was their first return to Mars in nearly 15 years, and their first sample return attempt ever. The loss triggered widespread criticism within Russia. Officials questioned whether the nation's space agency, Roscosmos, had the capacity to manage complex deep space missions. A special investigation was launched. In the aftermath, there were talks of relaunching a new version of the mission, named Phobos Grunt 2, possibly as part of a joint program with the European Space Agency. But that follow-up never came. Budgets shifted. Attention returned to nearer Earth projects. For many years, Russia did not attempt another interplanetary mission of such scope. What remains of the mission is not just hardware scattered across the Pacific. There are also design documents, blueprints, and engineering test units stored in labs and warehouses. There are data records showing its short period of activity and orbital maps of its decaying path through Earth's sky. And there is the memory of what was tried, what was planned, and what almost happened. ISRO's Mars Orbiter mission, still whispering from afar. In November 2013, at the Satish Dhawan Space Centre, a rocket lifted off carrying India's first interplanetary spacecraft. The name of the mission was straightforward, the Mars Orbiter Mission, or MOM. This was India's first attempt to reach another planet. A newcomer to deep space exploration, ISRO, the Indian Space Research Organisation, was stepping into a field dominated by giants, NASA, Roscosmos, and the European Space Agency. And yet, it made history. MOM was built on a modest budget. Reports often compared its cost to that of a Hollywood movie, around $74 million. For a full planetary mission, complete with launch, transfer, orbital insertion, and science operations, this was unheard of. MOM was designed, built, and launched within a span of less than 2 years. That speed, combined with its frugal nature, earned it both admiration and skepticism in the early days. The spacecraft was launched aboard a PSLV-XL rocket, the most powerful version of India's workhorse launcher. Since the PSLV couldn't send MOM directly to Mars, the spacecraft had to first perform a series of complex maneuvers around Earth, apogee-raising burns, before escaping Earth's gravity. Each maneuver pushed the spacecraft's orbit higher until it finally broke free from Earth's grip and began its 300-day journey to Mars. MOM arrived at Mars in September 2014. As the spacecraft approached its target, tension filled the ISRO control room. One critical maneuver remained: Mars orbit insertion. If anything went wrong, if the main engine didn't fire, if the spacecraft turned the wrong way, if the calculations were off, the probe would sail past Mars forever, lost in heliocentric orbit. But the maneuver went smoothly. The engine fired for the required duration. MOM slowed down and fell into orbit around the red planet. India had done what no other country had achieved on its first attempt: a successful Mars mission. Even the United States had needed a few tries to get it right. The Soviet Union had struggled. Europe's first Mars mission had failed to land. But India, with its first interplanetary spacecraft, had reached Mars and had gone into orbit. MOM carried 5 scientific instruments. One was a color camera to image the Martian surface and atmosphere. Another was a methane sensor, searching for possible signs of biological or geological activity. There were also instruments to study the upper atmosphere, surface features, and dust. MOM's science goals were modest, especially compared to missions like NASA's MAVEN or ESA's Mars Express. But its value was in something more fundamental. It was a proof of capability, a working example that a newer space power could do what many once thought impossible: For years, MOM took images, recorded data, and relayed it back to Earth. Some of its images were shared widely, shots of the Martian disk with the polar caps visible, cloud formations over ancient craters, and surface details seen from afar. Its camera wasn't as powerful as others, but its perspective was unique. MOM was designed to last for about 6 months. It remained active for several years, continuing to send data and monitor conditions in Mars orbit. Engineers adjusted its orbit to extend its life, tweaking its position as the seasons on Mars changed. By the time it reached 2020, it had long outlived expectations. But then, in 2022, contact was lost. ISRO officials later explained that the spacecraft had likely run out of fuel. This would mean it could no longer maintain its orientation toward Earth and the Sun. Without proper attitude control, the solar panels wouldn't generate enough power. Despite efforts to regain contact, MOM remained silent. There were no final messages, no emergency beacons, no last photographs. Even now, MOM may still be orbiting Mars. Its trajectory was stable enough, and there's a good chance that the spacecraft is still circling the red planet, dark and unresponsive. It has joined the growing population of derelict spacecraft in Martian orbit, silent companions to Mars Odyssey, Marvin, and the others still operating. But MOM's presence is distinct. It is the only Martian orbiter from a nation that had never been to Mars before. It is the quiet signal of a new spacefaring country finding its place among those who came before. It no longer responds to commands, but it remains up there, proof of a time when India dared to reach across interplanetary space and succeeded. It trained a generation of engineers and scientists. It strengthened public interest in space. It gave ISRO the experience it needed to consider future planetary missions, including Chandrayaan-2 and its follow-up plans for Venus, and even a second Mars mission. While it was never designed to compete directly with larger and more complex missions, MOM achieved something equally valuable. It demonstrated that Mars was no longer off-limits to newcomers. With the right planning, careful use of resources, and a clear set of goals, reaching another planet was possible even for a country without a decades-old deep space program. MOM also highlighted how international space efforts were changing. The traditional space powers still lead, but they are no longer alone. Missions like MOM reshape the narrative, showing that exploration isn't limited to a handful of players. With each new mission, new voices join the chorus, expanding our understanding of the solar system and what lies beyond. Whether or not India launches another mission to Mars in the near future, MOM has already secured its place in history. The tiniest ghosts, CubeSats lost in the cosmic void. When the first CubeSat concept was developed in the early 2000s, few imagined how far the idea would travel, literally. Born from university labs and shaped by the dream of democratizing access to space, CubeSats began as small, box-shaped devices measuring just 10 centimeters on a side. They were launched as secondary payloads, hitching rides with larger missions. Their goals were simple: test hardware, monitor conditions, collect basic data. But over the next 2 decades, CubeSats began to evolve. Some left Earth's orbit entirely. Some aimed for the Moon. Some tried for Mars. And some are now gone, lost in the silence of deep space. CubeSats are not built like traditional space probes. Their design is simple, modular, and limited by size. A single unit, known as 1U, weighs around a kilogram. Larger versions, 3U, 6U, or even 12U, offer more space and capability, but they still pale in comparison to conventional interplanetary spacecraft. A CubeSat might be small enough to hold in one hand, but once it leaves Earth, it's subject to the same vast distances, radiation, and thermal extremes that challenge probes the size of a car. One of the first CubeSats to truly stretch the boundaries was MAR-CO, short for Mars Cube 1. These twin 6U CubeSats, nicknamed Eve and Wall-E, were launched alongside NASA's InSight lander in 2018. Their purpose was to relay data from InSight during its descent to the Martian surface, acting as a communications bridge during those crucial minutes. It was a test to see whether small satellites could survive the journey to Mars and perform a useful task. And they did. Both Mako units worked as expected, relaying signals in real time as InSight touched down. They took pictures along the way and proved that miniature satellites could play a role in deep space. After flying past Mars, both Mako units continued on into heliocentric orbit. They had no propulsion systems to adjust course, and their communication systems were limited. Slowly, their signals grew weaker. First Wall-E went silent, then Eve. Mission engineers tried to contact them for several weeks after their flyby, but eventually the efforts were halted. The tiny spacecraft were gone. Mako showed that CubeSats could be more than Earth-bound experiments. Other missions followed. When NASA's Artemis Y launched in 2022, it carried 10 CubeSats designed to perform a variety of tasks around the Moon and beyond. Among them were Lunar IceCube, Lunar HMAP, and Omotenashi, a Japanese attempt to perform a lunar landing with a CubeSat-sized craft. These missions pushed the limits even further, aiming for places that were once reserved for large, well-funded probes. But not all survived. Omotenashi failed to communicate after being deployed. A communications glitch prevented the small craft from receiving commands needed to initiate its descent to the Moon. Without those instructions, it never landed. Its exact fate is unclear, but it likely tumbled through cislunar space and eventually drifted into solar orbit. Another Artemis CubeSat, Lunar HMAP, was intended to orbit the Moon and study hydrogen deposits near the lunar South Pole. But shortly after launch, the CubeSat's propulsion system failed. Without the ability to adjust its trajectory, Lunar HMAP couldn't achieve lunar orbit. Like Omotenashi, it likely missed its target and floated away, another tiny ghost among the stars. Some of these CubeSats did communicate briefly before going silent. Others failed right from the start, lost before they ever had a chance to function. In a way, their small size makes them more vulnerable. A software glitch or hardware failure that would be manageable in a large spacecraft can be fatal to a CubeSat. They don't have the redundancy of traditional space probes. There is often no backup system, no second chance. Despite these risks, CubeSats continue to be launched with deep space ambitions. Their appeal lies in their low cost and fast development cycles. A student team or a small startup can design and build a CubeSat within a few years. For those who might never have the resources for a full-scale mission, CubeSats offer a chance to try. Even if they fail, the experience gained is valuable. For those that work, the rewards are enormous. With each launch, more of these tiny explorers become lost in the void. Some are now circling the Sun on quiet paths, forever disconnected. Some drift near the Moon or orbit Earth in elongated trajectories. None are tracked regularly after their signals go dark. They are too small, too scattered, too silent. Occasionally, ground-based observatories detect flashes or faint signals that may be remnants of long-lost CubeSats. But more often, there's simply nothing. Once their batteries drain and their solar panels stop producing power, they simply go dark. Many don't even have propulsion systems, meaning their fate is largely determined at deployment. CubeSats don't receive headlines the way Mars rovers or Moon landers do. They don't have high-definition cameras or names that people remember. But their contribution to space exploration is growing. They represent a new chapter, one written not only by nations, but by universities, companies, and small teams of engineers. Each silent CubeSat helps define the limits of what is possible, what works, what breaks, what needs to be redesigned. The failures inform the next generation. And slowly, over time, CubeSats are becoming more robust. Some now include propulsion. some can adjust orientation. Some are being designed with interplanetary durability in mind. As this field matures, the number of CubeSats in deep space will grow. More will orbit the Moon. Some will follow larger missions to asteroids or comets. Others may one day travel to Mars again. Each one will carry the lessons of those that came before, those silent cubes now drifting unseen between planets. Echoes around the Moon, the ghost of Explorer 49. In the early 1970s, a strange spacecraft was launched toward the Moon. This was Explorer 49, part of NASA's series of radio astronomy missions. Unlike most lunar orbiters, it didn't carry cameras or instruments for close-up imaging. It wasn't there to look. It was there to hear. And for a brief moment in time, it became the largest radio telescope in space. Explorer 49 was launched on June 10, 1973, as a follow-up to Explorer 38 and Explorer 43, satellites designed to study the radio waves emitted by deep space sources. These earlier missions had orbited Earth, but Earth itself was a noisy place for radio astronomy. The planet's atmosphere and human-made radio signals cluttered the air. Even on the dark side of Earth, the surrounding environment was full of interference. To get better data, scientists needed to go somewhere quieter. That quiet was found around the Moon, specifically behind the Moon. When a spacecraft passes behind the Moon from Earth's perspective, it's shielded from almost all of Earth's radio noise. The far side of the Moon becomes a natural barrier, a massive wall that blocks the constant hum of Earth's electronics, transmissions, and other interference. Explorer 49 was sent there to take advantage of that natural silence. To do its job, the spacecraft needed long antennas. Once in lunar orbit, Explorer 49 extended 3 enormous booms, each measuring 230 meters. These thin, wire-like arms gave the spacecraft the largest effective antenna size of any radio telescope in space at that time. The shape wasn't neat or symmetrical, and the deployment process wasn't smooth. But once the antennas were unfurled, Explorer 49 became something rare, a floating radio observatory beyond Earth's noise. Its mission was to map the sky in low-frequency radio waves, frequencies that couldn't be studied from the ground because Earth's atmosphere blocks them. These low frequencies come from some of the oldest, farthest, and most mysterious objects in the universe. Pulsars, quasars, distant galaxies, and cosmic background radiation all whisper in this range. Listening in on them could reveal patterns about the early universe, magnetic fields, and the behavior of particles in deep space. For 2 years, Explorer 49 circled the Moon in a highly elliptical orbit. It slowly gathered data on the low-frequency universe. Unlike visible light, radio waves don't paint a clear picture. They form noisy maps, full of static and broad, fuzzy outlines. But even these shadows told scientists something about what was out there. The spacecraft's data gave researchers new insights into galactic radio emissions and added to a growing body of knowledge about the invisible forces in the cosmos. By 1975, communications ended. The spacecraft had done its work. The long antennas, once precise listening devices, became dead weight. Orbital calculations suggest it presumably crashed sometime after. Explorer 49 holds a strange and special place in the history of space science. It was a pure science mission. No rovers, no return samples, no high-resolution images. Just data. Just cosmic whispers from ancient sources, gathered in a pocket of silence only found behind the Moon. Radio astronomers have long dreamed of placing large observatories on the far side of the Moon, away from Earth's growing electronic noise. Explorer 49 was a first attempt, a kind of proof of concept. It showed that listening from lunar orbit was possible and useful. Even with limited instruments, it expanded our reach into radio frequencies never before mapped in space. Today, new proposals still refer to Explorer 49 when talking about the benefits of far-side astronomy. It also stands as an example of how science doesn't always need big spectacles. The antennas it carried stretched out like ghostly threads, measured signals from beyond the galaxy. In an age of moon boots and Mars landers, Explorer 49 was quiet. It looked past the local and focused on the cosmic. Mariner 4's trailblazing gaze at Mars and its eternal drift. Mariner 4 was the first to show the world what Mars actually looked like. It was the moment humanity truly saw Mars up close. Launched on November 28, 1964, by NASA, Mariner 4 was part of the larger Mariner program. It was small by today's standards, less than 300 kilograms in mass, powered by solar panels and a modest antenna. Its mission was to fly by Mars, gather scientific data, and take photographs as it swept past the red planet. Previous attempts by the United States and the Soviet Union had all failed. Mars was proving a difficult target, far more challenging than Earth's moon or nearby Venus. Getting there required precise timing, powerful boosters, and equipment that could survive the deep cold of interplanetary space. Once launched, Mariner 4 began a long cruise phase. It drifted across space for over 7 months before finally reaching its closest approach to Mars on July 14, 1965. As it neared the planet, its instruments came to life. The most important among them was its television camera, a simple imaging system by modern terms. It took 21 images in total, using a slow scanning process to capture black and white pictures line by line, storing them on a small onboard tape recorder. These images were later sent back to Earth at a pace so slow that the process took weeks. But when the first ones arrived, the space community and the world watched closely. Mars, which had long been thought of as potentially Earth-like, appeared barren and harsh. Instead of oceans or green valleys, the images showed a cratered surface, dry and dusty, more like the moon than a second Earth. There were no signs of canals, no signs of life, and no clear evidence of atmosphere or water. For a public raised on science fiction and the possibility of Martians, it was a sobering view. But for scientists, it was a huge step forward. These were the first direct observations, and they set the stage for everything that came later. Alongside the images, Mariner 4 also collected data on Mars's atmosphere and magnetic field. It found that the Martian atmosphere was incredibly thin, mostly carbon dioxide, and less than 1% of Earth's surface pressure. It also detected no significant magnetic field, suggesting that Mars lacked the kind of internal dynamo Earth uses to protect itself from solar radiation. Once the flyby was complete, Mariner 4 had done what it was built for. It continued on its path, still functional, now drifting farther from Mars and into a long heliocentric orbit around the Sun. It had no propulsion system to adjust its course after the flyby, so it simply became another object moving through space. It passed through conjunction with the Sun, meaning it was briefly on the far side from Earth and could not communicate. But after that, engineers at NASA decided to continue using the spacecraft for as long as possible. For nearly 3 more years, they kept contact with Mariner 4. It provided data on the space environment, including information on cosmic rays and solar wind. Eventually, its instruments began to wear out. The onboard tape recorder failed, power levels dropped, and in late 1967, contact was officially lost. Today, Mariner 4 orbits the Sun once every 20 months or so, on a path slightly more elongated than Earth's. Its orbit carries it both closer to the Sun and farther away, reaching points near Earth's orbit and then stretching beyond Mars's. It does not come close enough to either world to pose a collision risk, and it has no systems active anymore. It is just drifting, a silent, inert witness to a past era of exploration. It's easy to forget how primitive spaceflight was in those early years. Mariner 4's camera system was operated using instructions programmed into it using early punch card logic. The images had to be read off the tape recorder, digitized at slow speeds, and then interpreted using printouts and paper strips. At one point, when the data was coming back slower than expected, NASA engineers took raw numbers from the spacecraft and used coloured pencils to hand draw the first picture. Even in the absence of the final photo, they wanted to glimpse what was waiting on the other side. That sketch, the first image of Mars ever seen by human hands, was grainy and crude, but meaningful. It marked the start of true interplanetary imaging. Mariner 4 showed that a machine could travel to another world and bring back real knowledge, not just theory. In many ways, it was the beginning of robotic planetary science as we know it. If someone were ever to find it, perhaps in some distant future mission, they might see its weathered metal, its long solar panels now dark, and its antenna aim nowhere. They might recognize it for what it was, a machine that carried a glimpse across space, one that brought Mars a little closer to Earth. By showing us the surface of another world for the first time, it forever changed what we imagined was possible. The TRS-80 in the sky, the outdated computers powering abandoned probes. The computers used in early space probes were never meant to match the power of Earth-based systems. They were built to be reliable, durable, and efficient with energy. Most importantly, they had to survive the stress of launch, the vacuum of space, and decades of cold and radiation. These weren't general-purpose computers. They were tailored to specific missions, coded by hand, with programs loaded before launch and changed only when absolutely necessary. The software was minimal. The hardware was basic. But they worked. One example is the onboard computer used in the Voyager spacecraft. They each carried 3 separate computer systems: the command system, the flight data subsystem, and the attitude and articulation control subsystem. Each one handled specific tasks, from steering to processing scientific data to keeping time. The processors inside these systems had word lengths of 18 bits and operated at speeds that are barely noticeable by today's standards. The total memory available on board was just 69.63 kilobytes. That's less than the size of a single photo on a modern phone. These computers didn't even use silicon chips in the way we think of them today. Much of the memory was made using magnetic cores, tiny loops of wire wrapped around magnetic material. Data was stored by magnetizing the cores in a specific direction. Reading and writing were done through tiny electrical pulses. It was a technology from an earlier time, chosen not because it was fast, but because it was stable, non-volatile, and resistant to radiation. These machines were designed to last, and they did. Voyager 1 and 2 are still talking to Earth. Their computers are still receiving commands, executing sequences, collecting data, and sending it back. In recent years, engineers have had to work around failing hardware, rewriting software routines to bypass broken sections of memory, and reprogramming systems to extend their lives just a little longer. These ancient machines, through care and patience, have been kept alive far beyond their expected limits. The Pioneer 10 and 11 spacecraft also carried onboard computers of modest power. Pioneer 10's guidance and control system used what's known as a Command and Data Handling System, or CDHS, which was primitive by later standards. It could store only 5 commands at a time. These commands were sent from Earth and queued up for execution. There was no autonomy. If a problem happened and Earth was out of contact, the spacecraft couldn't correct itself. Yet even with these limitations, Pioneer 10 operated for more than 30 years, before finally going silent in 2003. What connects all these spacecraft is their slow, steady processing speed and the simplicity of their design. In many ways, their computers resemble those found in the earliest personal computers, like the TRS-80, Apple II, or Commodore PET. These home computers, famous in the late 1970s and early 80s, had similar limitations. small amounts of memory, slow processing, no multitasking, and text-only interfaces. But they also had something else: predictability. They were systems that didn't crash without reason. They did what they were told, step by step, in ways that engineers could fully understand and manage. This predictability is what made them perfect for space missions. Space is an environment where failure is costly and repairs are impossible. A spacecraft can't blue screen or freeze and expect someone to reboot it. That's why engineers chose these older, simpler systems. They could be tested thoroughly. They didn't depend on large operating systems or third-party code. Everything that ran on them was built in-house, purpose-made, and tested under every possible condition. Of course, these systems had limits. The low memory meant that science data had to be compressed or recorded in small chunks. The low speeds meant that high-resolution images took hours or days to send back. Commands had to be carefully written and checked before transmission, because even one wrong instruction could put the spacecraft in danger or waste valuable time. There were no backups in the modern sense. Everything had to work the first time. As time passed, newer spacecraft moved on to more modern systems. The Galileo probe to Jupiter used processors based on the RCA 1802 chip, the same type used in some early home computers. Later missions like Cassini and the Mars rovers used radiation-hardened versions of PowerPC processors and advanced memory chips. But even today, many space missions avoid the bleeding edge. They use hardware that's years behind consumer tech because stability still matters more than speed. Space favours the tried and true. These old computers are reminders of a time when engineering was constrained, but also elegant. The code they run is lean, written in assembly language by small teams of programmers who had to think in bits and cycles. There were no fancy graphics, no extra features, just pure functionality, built to survive in a harsh environment with no second chances. If one were ever found by another civilization or by future humans, they would be like digital fossils, preserving a snapshot of Earth's early space age. Inside their circuits, frozen in time, are the ideas and hopes of the people who sent them out. They may not be powerful, but they have travelled farther than any other man-made object. They have seen planets, crossed interstellar space, and outlived their designers. In a world that often values the new and fast, these machines stand as a quiet counterpoint that sometimes simple and steady is enough. Do ghost satellites interfere with space exploration today? Space exploration has always depended on carefully mapped orbits. Every working satellite, telescope, or crewed vehicle must pass through regions crowded with objects, both alive and dead. The answer to whether ghost satellites are a problem is, more and more, a yes. These derelict machines can get in the way, they can cause damage, and sometimes they force working missions to make emergency moves to avoid a possible crash. Most ghost satellites come from earlier eras of spaceflight, when disposal wasn't always a priority. In the early days of space exploration, there was little concern about what would happen to satellites after they stopped working. In low Earth orbit, or LEO, atmospheric drag can eventually pull a satellite down, burning it up in the atmosphere. But in higher orbits, such as medium Earth orbit, or MEO, and geostationary orbit, or GEO, a satellite may remain practically forever. In 2009, the risk turned real. An Iridium communications satellite crashed into a defunct Russian satellite called Cosmos 2-251. The two collided at high speed, over 26,000 miles per hour. Both were destroyed. The impact generated more than 2,000 trackable pieces of debris, each one capable of damaging or destroying another spacecraft. This collision was a wake-up call. It proved that ghost satellites are hazards. Space agencies now track thousands of defunct objects in orbit. The US Space Surveillance Network catalogues more than 25,000 tracked objects, but many more are too small to see with radar. These include paint flecks, broken bolts, and fragments from earlier explosions or collisions. Together, they form a cloud of space junk that threatens modern missions. The biggest concern isn't usually large satellites, which are easy to track. It's the smaller, fast-moving fragments that pose sudden danger, but even intact ghost satellites can drift into trouble. When a working spacecraft plans its path, it must check for possible conjunctions, moments when it might pass dangerously close to another object. If that object is a defunct satellite, there's often no way to communicate with it or steer it out of the way. Active spacecraft, like Earth-observing satellites or crewed missions, sometimes have to perform what's called a collision avoidance maneuver. This uses fuel, time, and computer resources. The International Space Station, for example, has changed its orbit multiple times to avoid debris from dead satellites or rocket stages. Every time this happens, mission planners must adjust schedules, experiment plans, and resupply coordination. When satellites in GEO reach the end of their lives, operators are now expected to move them into a graveyard orbit. But not all older satellites were moved. Some lacked the fuel or capability. Others were abandoned before graveyard protocols were in place. As a result, GEO has its own collection of motionless sentinels from earlier decades. Modern mission planners must account for them. Before a spacecraft is launched, teams simulate thousands of possible trajectories to avoid known hazards. They check orbital data regularly, updating their models. In some cases, a collision risk is found just hours before a close pass. The avoidance maneuvers are then calculated quickly, with little time to spare. Governments and private space companies have also begun discussing better solutions. Ideas include active removal, using robotic craft to push dead satellites out of the way, or using nets, harpoons, or lasers to slow them down. Some research teams are developing small spacecraft that could attach to ghost satellites and drag them into the atmosphere for safe destruction. But these missions are complex, expensive, and politically sensitive. A satellite removal craft can look very similar to an anti-satellite weapon. That has slowed cooperation. In low Earth orbit, mega-constellations like SpaceX's Starlink add another layer of concern. These networks involve thousands of satellites launched in tight formations. Though most are active, even a few failures could create long-term risks if the dead units can't be deorbited. Ghost satellites that pass through these layers could cause cascading collisions, a feared scenario called the Kessler syndrome, in which debris causes more debris in a chain reaction. For now, most ghost satellites are not causing daily disruptions. They remain background risks, known but passive. But the numbers are growing. Each new launch adds to the population in orbit, and not every mission ends with a clean deorbit or disposal. Some ghost satellites are still studied for research purposes. Their orbits help test tracking software. Their surfaces offer insights into the long-term effects of space weathering, micrometeoroid impacts, and radiation. A few are even used to test ground-based laser communication systems, bouncing light off their old surfaces. But none of that changes the basic truth. They are inactive, and they are in the way. In the decades ahead, managing this space debris will become a priority. Already, nations are creating guidelines for space traffic management, similar to how air traffic control works on Earth. But unlike airplanes, most satellites cannot be steered once dead. Each one represents a lesson in how long things can last once left in orbit. Each one shapes the decisions of new missions. Who keeps track of the forgotten ones? The role of deep space networks. Keeping track of inactive spacecraft and other space debris is not an easy task. It requires powerful radar systems, precise mathematical models, and careful coordination between nations. But for spacecraft that travel far beyond Earth orbit, for those in deep space, tracking becomes even harder. Even those who launch them have lost their grasp on exactly where they are. The responsibility to track such distant objects falls to a small number of specialized systems, the most important of which is known as the Deep Space Network, or DSN. Operated by NASA, the Deep Space Network is a global system of radio antennas that can communicate with spacecraft many millions, or even billions, of miles away. The network consists of 3 main sites, one in Goldstone, California, one near Madrid, Spain, and one near Canberra, Australia. These locations are spaced evenly around the globe so that at least one can always see any spacecraft that is in the sky above Earth's horizon. The DSN was built to support active missions across the solar system. It helps guide spacecraft during planetary flybys, collect data during landings, and transmit scientific information back to Earth. But once a mission ends, once the spacecraft is shut off or fails, the need for constant contact usually ends as well. That's when these crafts become harder to follow. Some old spacecraft remain easy to track because they follow known orbits. Even without communication, scientists can estimate where they are by using the last known position and velocity. Gravitational models and orbital mechanics help predict their paths, but the longer it has been since a spacecraft was active, the more uncertain those predictions become. A small change in velocity caused by something as simple as a gas leak can alter an orbit. In deep space, even a tiny shift can become a large error over time. If a spacecraft has gone completely dark, tracking it depends entirely on ground-based radar or optical telescopes. In Earth's orbit, radar systems like those operated by the US Space Surveillance Network can track objects as small as a softball. But in deep space, radar becomes much less effective. The distances are simply too vast. The signal strength needed to bounce radar off a probe near Jupiter, for example, would be enormous. And most of these defunct spacecraft are too small and too far away to reflect much signal back. Some nations maintain lists of known space objects, including many that are inactive. The United States keeps a public catalogue through entities like NORAD and the US Space Command. Other countries, including Russia and China, maintain similar databases, although not all information is publicly shared. These catalogues focus mostly on Earth orbit. When it comes to deep space, many objects are simply marked as lost contact or status unknown. There are also growing efforts in the private sector to improve space tracking. Companies like Leo Labs, Astroscale, and Exoanalytic Solutions use networks of ground-based sensors to watch for space debris and inactive satellites. However, these efforts mainly focus on near-Earth space, particularly low Earth orbit and geosynchronous orbit, where most commercial traffic operates. Very few private entities track anything in interplanetary space. When an old spacecraft like Voyager 1 or Voyager 2 is still active, it remains part of the DSN's regular schedule. But even for those missions, time is limited. The DSN serves many missions at once. Antenna time is precious. Engineers must carefully schedule when each antenna is pointed at a given spacecraft. For the Voyagers, contact windows are now limited to just a few hours a day, and the signals they send are extremely weak. When contact is lost completely, some spacecraft are intentionally forgotten. Mission teams may try for weeks or months to re-establish a signal. If no response comes, the mission is declared over. But declaring a mission over doesn't mean the spacecraft vanishes. It just means we've stopped listening. In rare cases, decades later, a signal might be rediscovered. That happened with NASA's IMAGE satellite, which went dark in 2005 and was unexpectedly found transmitting again in 2018 by an amateur radio operator. Engineers scrambled to make contact again. For a short time, the satellite came back to life, until it went quiet once more. Most spacecraft are not so lucky. They go silent and stay silent. And while their physical presence continues, they no longer get any attention. The DSN does not waste time scanning the sky for ghosts, It focuses on missions that still have goals and instruments and working transmitters. That leaves many old probes drifting in silence. How much effort should be made to track something that no longer functions? The data collected by these missions already helped shape scientific understanding. Their value was in the information they gave us while alive, but their bodies remain out there. Does that make them space debris? Or are they historical monuments? Even when these far-off probes are no longer tracked, they remain in motion. Some follow heliocentric orbits, circling the Sun like tiny planets. Others are headed out on escape trajectories, pulled ever farther from the Sun, beyond the influence of the solar system. These are the most unreachable of all. For all practical purposes, they are lost to us. The DSN and its partner systems track the living missions, guide them through space and listen to their last signals. Sometimes those signals come just before shutdown. A final whisper, a data dump, a goodbye from a craft that knows its time is done. The DSN logs it, stores it, marks the mission as ended, and then the network moves on to the next. But even then, somewhere in the logs, the name remains, the last known coordinates, the orbital path, the frequency it once used, a little trace in the records that this machine existed and that someone once cared where it was. And perhaps in that quiet bit of bookkeeping, the forgotten ones are remembered after all. And on that bittersweet note, this video must come to an end. What other idea would you like for us to cover next? Comment down below, and if you enjoyed this one, consider leaving a like and subscribing. Thanks for watching.